Artificial intelligence refers to the simulation of human intelligence in machines that are programmed to think like humans and mimic their action. The term may also be applied to any machine that exhibit traits associated with a human mind, such as learning and problem solving. In this tutorial, you will learn about the various projects that you will make, starting from how banks default using ANN and how intuitive deep learning can be used for stock prediction. So fasten your seatbelt, as now you will see the magic of artificial intelligence in its totality. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments. So very quickly, let me walk you through the agenda for today's course. In today's course, we are going to look at bank defaulters using ANN, stock price prediction using deep learning, and artificial intelligence projects.
So first we will start with what is image processing. So we all familiar with image, right? So we actually process the image to do some operations, right? And to do some operation, we need to extract some information from those images, right? So in that case, image processing come into the picture. So when I'm talking about, I need to differentiate between dog or a cat image, right? So it's not possible by looking at the image for computer to understand what is the dog image and what is the cat image. So in that time, we need to go for image feature extraction. And with those features, the features for dog image and the features for cat image is not same, right? So that difference help a computer to understand that what is the difference between those two images. So this is how actually image processing stands for. So it is one of type of signal processing. So if you guys from ECE background, electronics background, so you should have idea that what is a signal processing, or who doesn't have idea, so I can give a little one-liner that signal processing basically the way we talk, right? So your voice, so that voice also can be processed to do some text to speech or some other applications as well, right? So this is one type of a signal processing. In this processing, input is an image. So for image processing, our input is an image and output is also an image or a characteristic or features associated with that image, right? Okay. So then have a look at an image, right? So maybe it's a dog or cat. How can you do that? So using machine learning to understand that an image is a dog or cat, that is a problem, because in an image, there is a dimension. When we talk about the dimension, there is a lots of dimension we will get. But from a, like in machine learning, what we need to do a manual selection. But manual selection is a huge dimension, right? So it's not possible. So in that case, deep learning come into the picture. And deep learning help us to do those feature extraction part, right? It helps us to actually identify which feature is actually help our model to work with, right? So in that case, deep learning came into the picture. Now we will have a look at when we talk about neural network, right? So what is the difference between human brain and the neural network? We all know this, that a human brain is like the neural network is like a human brain. Most of them who actually starts their career or who starting learning this human brain and neural network, artificial intelligence, they have that doubt in their mind that how actually this neural network can be a human brain, because human being is actually a complicated version, right? So in that case, there are some part we actually can consider and compare with human brain with the neural network, right? So in that case, our human brain has dendrite, our human brain has axon terminals, but in the neural network, what we have activation function, we have input layer, we have hidden layers, right? So basically we have three parts in a neural network. Artificial neural network, basically we have a hidden layer, we have input layer and we have output layers. So this hidden layer is actually working as a black box thing. So if you don't know the mathematics behind that, so in that case you can say it's a black box. But if you know the mathematics behind this, so it is not a black box. This is one myth we know, that artificial neural network is a black box, but it is not a black box. It is a proper mathematical implementations, right? So basically scientists want to make a artificial neural network that works as our human brain works, right? So it is quite similar with that, but not fully similar with that. Now we will have a look at what are the thing we have in our human brain, for that we can compare with the artificial neuron. So in that human brain we have cell nucleus. So in that case, artificial neural network have node. In human brain, we have dendrites, right? So in the artificial neural network, we can replace them with input layer. That's the inputs, right? X1, X2, X3. Okay. In human brain, we have synapses. So how can you replace that synapses out artificial neural network? So in that case, we use weights or interconnection. This weight and bias helps us to actually calculate the inputs. This is the main part for an artificial neural network. Now we have axon in our human brain. So in that case, neural network has mapping, activation and learning. So lastly, we have terminal axon. And for the artificial neuron, we have output. That output layer. Why go for human brain versus neural network? So basically, we all know that neural network is basically a replica of human brain, right? So who are actually new to this domain, they want to know what is the similar thing we have in human brain and neural network, right? So in that case, I just want to clarify you guys that what are the thing we have in human brain and what are the thing we have in neural network, and how can we compare them, right? Okay, so let's have a look at how a computer can see a image. So computer cannot see a image because computer doesn't have eye, right? So in that case, computer converts those images into an array of pixels, values. You can see this is a dog image, but for a computer is like, I don't know what image is this, right? So in that case, computer can see only the pixels, and that pixels is actually help us to do this processing, this image processing, right? So here you can see it's a color image. So for that, the dimension of this color image is 3. So if we have a image like a black and white image or a gray image, so that time the dimension should be 2. Right? So this is the one main catch point when we start working with any image processing. So if you want to go for doing any image processing, that time you need to convert your colorful image to black and white image, right? So this is how our image can be seen by a computer, right? It's a array. It's a numbers for the computer. They don't understand the image, right? Now we will see what is CNN. So CNN is stand for Convolutional Neural Network, a feed-forward network to process and recognize image data with a grid version. So what is that grid version? So this grid version is this part, right? This pixels. So we can say the pixel, through the pixel, a computer can see an image, right? Okay. So first we have an input layer in CNN, then we have a convolutional layer, then we have pooling layer, and lastly we have a dense layer, that is a fully connected layer. And lastly we got an output that is in a form of probability, right? So if the probability near to 0, so we can say, so this image is not belongs to cat, right? If the probability is 0 for the cat, and if the probability is near to 1 for dog, we can say maybe this image is a dog image, right? So this is how we use our convolutional neural network. Okay, so why it is 3-dimensional? So basically in the 3-dimensional, we need to go for color image. When our image is colored image, that time we have a RGB values, right? Red, green, right, blue. So in that case, we need to go for RGB values, and for that it is 3-dimensional. And when we have a gray color, right, or a black and white picture, that time we have 2 dimension. So now we will have a look at what are the layers we have in convolutional neural network. So we first have convolutional layer, then we have ReLU layer, then we have pooling layer, and then we have fully connected layer. So we have 4 layer in convolutional neural network to process our images, right? So in that case, first what convolutional neural network does, right? So let's have a look at one by one. So first layer is convolutional layer. So what convolutional layer does? So I told you that an image is already converted to an array. By that array, a computer can see those arrays, right? So convolutional layer help us to convert those images into an array, the first layer of CNN, and stores the pixelated values of image into an array, right? So this is the first layer actually help us to do the image processing, okay? And this layer is used for extracting the features of the image and reducing the dimensionality. So how we can do that? Let's have a pictorial visualization for that. Suppose I have an image, a dog image. So what are the pixels I have? I have 4, 21, 54, 92, 48, 2, 20, 2, 54, 36, 22, right? So in that case, what I need to do, I am going to use a filter. So when I start learning convolutional neural network, I actually got a big confusion that how these filters are going to use. So these filters are used randomly. There is no hard and fast rule. This is where your filter can be made, right? So in that case, our filter is 0, -1, 1, 1. So if you want to use a 3 cos 3 filter, I use a 2 cos 2 filter, right? So if you guys want to use any filter, right, and then values can be anything. So why we use this filter? We use this filter to reduce the dimension of the images. So in this case, the dimension of the image is very low, right? But when you have a HD picture, right? So we all like have a HD picture or a very high quality picture, right? So in that time, the image array will be a big one. So you are not able to work with those big arrays, right? So you need to reduce them. You just need to take the extract of that array, where your for this case you can see 22, 54, 36, right? These are the part of your image are actually having the actual image of a dog. So this is the basic part. This is the main important part of your image. So using filter, we try to extract those part. We try to extract that whatever the places we have in the image, they are actually highly featured. So in that, those parts we want to take and we want to process our images, right? If you can see, I have this part, right? 421 to 224 22, right? So what I have a 2 cos 2 matrix, right? Now what I need to do, I need to multiply with 4 into 0 plus 21 into -1, then plus 2 into 1, then plus 22 into 1, right? And then I will get a value for that, right? Now we will have a look at activation layer. So what is the activation function, right? So when we actually do some convolutional part, that time we have an input, right? From that input, we need to go for checking that if we have any minus or negative number or not. So we actually consider that if your pixel value is high, there could be a chances there will be some feature in your image, right? So in that case, what we do in the activation function, that is ReLU, we use ReLU. What ReLU does, it converts negative values into 0. So I already told you that if a pixel value is high number, right? So in that case, we can say there can be a feature, right? So in that case, you can see I have 87 over here, right? So 87 and 139. So I can consider this 87 and 139 has some feature, right? In the case of -2, we can say there is no feature because this is already belongs to -2. Okay, so in that case, we can say that, okay, this is -2, so there is no point of using this. So we can convert it to 0. So this is how we use ReLU layer. Okay, and whatever our pixel value is, we can say this is some of the feature is there in our image. Okay, so here you can see This is why we use activation function. Now you can see I have a minus value, that is -2, and my value layer, what it does, it convert that -2 to 0, right? So in that case we are using ReLU over here. So first we use convolutional layer. That convolutional layer help us to do the reducing of the image, okay, the dimension of the image, and getting the feature from the image. Then we go for ReLU layer just to eliminate all the negative value from our image array. So there is no point of processing minus values over there, right? So we convert them into 0. Now we will have a look at the pooling layer. So what pooling layer does? So reduce the spatial size of the number of the parameters, right? So now I have some of the parameters, right? Now we will have a look at the pooling layer. So pooling layer actually help us to reduce the spatial size and the number of parameters. And this pooling layer actually help us to reduce the dimensionality as well, and helps to control the overfitting. So if we have so many pixel values, and if we want to train our model with that, my model can be overfitted. What is overfitting? Your model will start learning each and everything from the training data set, right? But when you give a testing data set to your model, it will start saying, I don't know what will gonna happen, right? So in that case, for the training data set, it will give you maybe 99% accuracy, right? So your model start reminding those, not learning those parts, right? So in this case, for pooling layer help us to do not to overfit our models, right? And normally we use filter size 2x2 for pooling layer. Okay, now let's have a visualization of how pooling layers work. So we got 3, 22, 0, 10, 23, 25, 87 and 139 matrix. Now we are going to use 2x2 pooling layer. But what is stride? Stride is basically how your matrix is going to move, right? If your stride is equals to 1, it will go by 1 column. If your stride is equals to 2, it will go like after 2 columns, right? This is how your strides works. Okay, now what I did, I use a 2x2 matrix. So from that you can see 3, 22, 23, 25. I use the max number from the matrix, because this number help us to understand, okay fine, this is 25, there will be a feature, maybe there is a feature in the image from there, right? So I took 25. Now I just shift my matrix 1, because my stride is equals to 1. What I did, I use 22, 0, 25, 87. From this, which one will be the highest? 87. So I took 87, right? Okay, now we will have a look at, you can see I got all the high range featured from the images, right? Now I have only 4 image pixel, right? So I don't need to process a lot with this. So this is why we are using this layer of CNN to actually reduce the number of pixel, and that will help us to actually process those images, right? Now we will have a look at flattening the data. Now this data can be 2D data or can be 3D data, right? But what is flattening the data? So converting pooled feature map into an array is known as data flattening. So let me give you a proper example for that. So I have a 2D data, but in CNN, when you want to use a CNN algorithm, that time they will not take any 2D 3D data. That time it will only take a 1D array. So flattening is basically done to flattening your data to 1D, right? So this is how we use flattening of data. I got so many questions, let me answer a few of them. Okay, so can you give one example of pooling layer? I already give that. Won't there be one value repeated always after pooling? So basically why 139 is repeated, right? So you can see when I'm just shifting my stride, when I came to the last stride, right? So there is no other value. I have only 110 and 139. So this is why I took 139, right? This is how it actually works. How many types of pooling layer? So we have 3 types of pooling layer. Okay, sum pooling, average pooling and max pooling. I use max pooling over here. Do we need to decide the stride value as 1 or 2? Yes, you need to decide your stride value. From that only your image feature is actually extracted. Okay, so is there any relation between data encapsulation and data flattening? No. So basically data and encapsulation is encapsulating your data, and data flattening is basically flattening your data from 2D, 3D to 1D, right? Okay. So now let's have a look at the last layer we have in CNN. So lastly, we have the combination of last layer, that is fully connected layer. So now I have 4 pixels, right? So I can process them. That will not take a long time to process them. So in that case, what I do using fully connected layer. In that layer, what I do, I reduce the dimensionality. It helps to control overfitting, and it also filter size can be 2 cos 2. Now let's have a look at the fully connected layer. So you can see whatever the input I have, that is 25, 87, 139, 139. Why are we making the data into 1D array? So this is the basic part, right? This is the basic thing. When you actually want to process your image, that time your array should be in the 1D array. So you guys will be cleared after seeing the code. So in that case, you can understand if we don't flatten my data, that time it will not take your input. Okay, fine. Now let's have a look at our demo part. This is the most interesting part. I really love to do demo on these things, right? So here I'm going to use Google Colab. So if you guys want to know that how I actually use a Google Colab, let me show you that Google Colab. Go to Google Colab. This is actually featured by Google. Go there and click on Google Colab Notebook. So you will get, Google Colab, right? So you will get the first link for that. Go for Google Colab. Why I am using Google Colab for this session? Because we need GPU. So what is GPU? GPU is a graphical processing unit. It helps us to process our data. Because we are using image over here, so in that case, we need to have a proper GPU. If you don't have GPU, it will take a long time, guys, and we are actually have the time crunch over here. So if you don't have if you don't have GPU in your system, I should suggest you go for doing this thing in Google Colab. This is actually helpful. Okay, fine. Now what I need to do, I need to go to new notebook. Right? So when I go to new notebook, that time you will get an option to change your runtime to GPU. So you can see there is an option of runtime. You need to click over there and just write change runtime. So you will get 3 options, that GPU, TPU and none. So normally default it is in none, but in this case you need to go for using GPU, right? So go for GPU and then save. So it will help you to actually do this programming with a very short time. Okay, maybe for the none it will take a long time, but for the GPU it will actually help you to process your images. Okay, so let me go back to the code. Yes, so see, I just show you this is reconnected. Why it's reconnected? Because it's taking a lot of memory, right? In that case, Google Colab is not able to handle that. Right, so I always prefer you guys to go for Google Colab and using GPU. Okay, now let's have a look at the problem statement. So we have the dog versus cat dataset is a standard computer vision dataset, right? So in this part we will see how can you actually determine between dog and cat, right? So in that case, my class 1 is dog and my class 2 is cat. Okay, so you can see there is a nice G5 used to you guys understand that how actually convolution neural network works and how you can actually use them, right? OJAS is TPU processing. So TPU is basically used for some other cases, but if you want to go for image processing, I can suggest you go for GPU. You don't need to go for TPU. That's not even required, right? So now what we will do, so first, I already have my dataset in the Dropbox and I just want to fetch that. To fetching those data, I'm going to use wget command, right? So already I have fetched those data. I have 2 datasets, that is training dataset and testing dataset. So let me just show you what I have. Okay, I will show you that what I have in the dataset. And my dataset is in a zip version. I want to unzip them. How can I do that? To do that, I'm going to use unzip. unzip command, and then the zip file I have, that is training set.zip. So this is how we actually unzip our data, right? So you can see our data is unzipped, and I have a lot of data of dogs, right? I have a data of dogs and cat as well. So I am going to show you my data format, what I have. So you can see I have a test set, I have a training set. So let's go to that. You can see in that I have two folder. I have cat folder, I have dog folder, right? So in training dataset, I have two folder. One is cat, one is dog. And for the testing purpose also, I have two dataset. So I have two folders, sorry. One is cat, one is dog, right? So this folder will be my classes. So you can see dog and cat. This is also dog and cat. So this will be my classes. Okay. Okay. Now I want to show some of the images from that. So I am using matplotlib MPIMG. So matplotlib is basically used to visualize image. So instead of matplotlib, you can use OpenCV as well, right? So for that, there is a function called IAMRead. Okay. So this IAMRead, and then you need to provide the path of your image, right? So in this case, I use this. Or if you want to take a path, let me just open that. So in that case, you can see there are a lot of cat image I have, and just copy any of the path from there, right? So here I have this. Maybe you can use something another, right? Control V. Let me just do that. Yes, you can see I got some other image, right? So you can take any of the image from the cat folder and or the dog folder, and you can just see that how your image is actually working, right? Now what I did, I actually take a image from dog folder as well, right? So there are lots of image we have. Okay. Okay. So you can see I got a taste. I got a image from a taste set, right? So this is also, it's showing that yeah, I have two folder, and that two folder also have a dog and cat image. Okay. Now what I need to do, I need to import the library. So here I am going to use Keras. So Keras is basically built top of TensorFlow. So this Keras and TensorFlow are used to do image processing or any kind of, like if you want to make a model or deep learning, right? So in that case, what we do, we used to go for importing TensorFlow of Keras. Right? So my model will be a sequential model. Always the recurrent neural network, convolutional neural network, they are part of sequential model part. Right? Then what I did, I take the import of layers. What are those layers? I told you that fully connected layer I have. So this fully connected layer in Keras known as dense layer. Right? Then I have convolutional 2D layer. Okay, so in the convolutional 2D layer, so that is a convolutional layer, right? Then I import flatten layer, right? So I told you what are those flatten, convolutional layer and dense layer. Then I took a max pooling 2D. So I told you that pooling layer, right? So I use max pooling, and I importing also max pooling 2D. Okay, then I import activation layer, and what is dropout. So dropout is basically preventing your data from the overfitting. Your model will not be overfitted, right? So for that, it will suddenly drop out your neurons, right? So the neuron, the input layer we have, the input suppose 25, 36, 37, suddenly dropout will drop any of the neurons. Just for that, your model will not start reminding it, right? So in that case, we took dropout. Now, if you want to see the version of the TensorFlow, you can see this is 2.2.0, right? This is the current version of TensorFlow. Then what we did, we given a image width and the image height, right? So for that, I say that I want the image width of 150. Now we will have a look at that image width. So my image width is 150 and height is 150. I mentioned that. If you guys want to go for some other one, you can go for it. Then I define the directory of my data set. So my directory will be, if you want to take the directory, you just have to go there in the main folder and then copy path. Right? So I have training set of folder, and under training set I have again one more folder, that is training set, right? Then I say there will be epoch of 20 and batch size of 20. So what is epoch? Epoch is basically help you to suppose doing a work, repeating a proper cycle again and again, right? So my case, the training part will be continued till 20. So 20 times my data will learn from the data. My model will learn from the data. This is how we use epoch. And batch sizes, so your model will not learn the whole data set at a time. So batch size help us. So I said take 20 sample from my data set and just train my model with that. And the next time take another 20 sample from my data set and then start train my model again. So this is how we use epochs and batch size. Now I am going to check what is the channel of my data. So what is channel? So basically channel is representing two ways. One is channel last, one is channel first. So if image data is represented in a three-dimensional array where the last channel represents the color of channel, right? So how many color you have? 3, 2, 1, what you have, right? And then rows, columns and channels, right? So when you use channel last and if you use channel first, right? So that time if I have 3 channel, so it will 3 is specifically for RGB value. So we use 3, 2, 1. So my rows is 2 and column is 1, right? So this is how, okay, this is how we use this channel first. So I want to check my data, my image, what is the channel I have, right? If k.image_data format equals to channel first, right? Then what you need to do? Input shape equals to 3 image width, and I want my all of the image should be in a channel first data, right? So this is how we did it, right? Next, what we need to do? We need to go for generating train model. So one image, from one image, your model is going to build 3 to 4 images to get the edges from there, to get the features from there, right? So you can see I have one image, but I have so many other images. So this is how our image generator works. Okay, fine. So in that case, what I did, I called image data generator function, where I said rescale equals to 1 by 255. So what is that? To normalizing my images. Then I said horizontal flip equals to 2, zoom range equals to 0.2. So you can see some of my images are actually flipped, some of are zoomed, right? So this is how our image data generator generate data. Okay, so I do this for train data generator and test data generator, both of the cases. And lastly, what I got, I am getting sure that my model, whatever the thing I am doing, it's actually working. How can you do that? So for that, you can see found 8005 images belonging to 2 class. For the test and for the training, I have 2023 data, right? So in that case, you can see that I have 2 class, dog and cat. This is right, and I have this much of images. So this is how your data generator are actually working. Now I want to see what my data generator done. So you can see my data generator what done. You can see some of them are actually zoom, some of they are actually rotate, right? So this is how our actually image data generator works. Now comes the convolutional neural network part. Now I'm going to build my model. This is the most interesting part. So how can you do that? Right? So in that case, I have 4 layers, we all know, right? So in that case, what we are going to do over here? First, we are going to call that my convolutional neural network is a sequential model, right? So in that model, now I want to add first layer. What was the first layer? First layer is convolutional layer, right? Convolutional 2D layer. Now, what I'm going to add? I am going to add an activation layer. So why we use activation layer? For what reason we go for activation layer? So we use activation layer to remove the negative part, right? To negative image pixel from our data, right? So this is how I'm going to use ReLU. Then we are going to use max pooling 2D, right? Here I'm saying that my max pooling will be 2 cross 2. Right? I think you guys can understand what I am doing over here. What I told you in the normal normal one, right, in this presentation, and what I'm doing in the code. So both are same, for that you guys can understand that, right? Fine. Viral 10, I will explain that. For filtering, we don't need to write filter over here, right? So what I said 64. What convolutional 2D 64 watt. So 64 neurons I want to get from the output, and 3 cos 3 is my filter value. I am using 3 cos 3 filter over here, right? Okay. Fine. Now then what I add a flattened data that will flat my data to 1D channel. Lastly, I have a fully connected data. That is, last channel will have 64, right? And when I have 64, then I said, no, I want one more ReLU. I want to check that is there any negative value is there or not. Okay. So in that case, I am going to use ReLU again, just to cut off the minus or negative value. Lastly, I use a dense layer of 1. Why dense layer of 1? This is a fully connected layer, and where you will get your output. This is the output layer, guys, right? So output dense layer will always have a neuron or nodes that is 1, right? Fine. So in that case, I use 1. And lastly, I use a activation function of sigmoid. Why I use activation function sigmoid? So always in the output we get a probability, not a proper number 0 or 1. So if your number is near to 0, we can assume this is not the image. If your number is near to 1, so that time we go for saying, okay, this is our answer of our model. So you can see I got my model summary. So I have the layer convolutional 2D, activation function, then max pooling, flattening, dense, and again these 3 I have added more just to get a more accuracy, right? Lastly, I need to compile my model. How can I compile my model, right? So in that case, I'm using dot compile. So my model is ready. Now in compile, what I'm going to write? I'm going to actually provide my data, right? Sorry. So in that case, I use model dot compile, and I'm using optimizer. Why we use optimizer? Optimizer help us to understand that maybe your data is not right. So in that case, optimizer help us to understand optimizing our input, right? Optimizing our model. And here I am using loss equals to binary cross entropy. And lastly, the accuracy matrix. And you can see I got the summary of that, right? And now lastly, I'm going to fit my model. How can I fit my model? How can I train my model? My model is actually compiled, but now I need to give the proper data set of our model, right? So in that case, we use dot fit generator function. You can see dot fit generation function fits the model on data yield batch by a Python generator, right? So this is how we use dot fit generator. And I'm going to provide training generator and epochs. Already I have mentioned that, right? So you can see in I gave 20 epochs. If you guys want, you guys can give epochs can be 25, 30, anything, right? So I am not going to execute over here because this actually takes time. So if you guys want to do that, please use GPU to do that, because it will take lot of time. So you can see the value accuracy. Lastly, I got 72.90. So if you add more epochs to it, maybe your model start working more tunedly, right? More finely. Okay. Lastly, I am going to see the accuracy curve, right? So you can say this is the plotting one. So already you get the accuracy at 0.7290. If you guys want to go for checking the curve as well, you can do that. Otherwise, you already got your accuracy, how your model is working. So you can see training part is this, and for the testing, it's working fine, but not too good, right? So maybe in that case, you can add more model to your model. So add more layer to your model. And one more thing I just want to let you know, guys, for convolutional layer, you can use any of the layer twice, thrice, anytime, any number of time. But be sure your data is not lost. But before just going for the output layer, you have to be sure you use flatten part, right? So without flattening your data, you will not get your output. Okay, fine. Now, lastly, I want to see the predicted image. Okay, so you can see this is actually a dog, but it's saying it's a cat. Let me try to do these things with some other one. Maybe for this image, this is not working. So let me check. Okay, so let me just copy the path. How it's going to work? Yes, now it's this case, it is showing it's cat, right? So this is the main thing. Like if it's 72% accuracy, maybe some of the time it's working fine, or some of the time it's not working fine, right? So this was our whole presentation, whole session. I hope you guys understand.
We'll try to understand what is a deep learning approach that we can apply and how it works. Especially, we'll focus on artificial neural network, or one of the foundational, algorithm in once we enter like into the deep learning, right? So let me go back to the slide here. Yeah. So what do we understand? Let's start with the actual neural network basics, and let's start with the architecture of the neural network. So if people who don't know about how the architecture of neural network works, or how the architecture of deep learning is, mainly there are two steps, or it's a two-step process that we follow in deep learning, right? The first is the forward process, or forward direction process, right? The second process is the backward direction. So we'll explore one by one what is these direction is all about. But if you see the graph, the images that are shown here, let's start with the left side graph. What we are showing here is there is an input layer, which is nothing but your input data, that passes to a layer called hidden layer. So that layer is not visible to us directly, because we know our input data and we know the output in a training model that we talk about. Hidden layer is a layer, basically a processor on our input data that we are applying. Processor means that what kind of patterns we want to detect on our input data so that we get the output. That is where the hidden layer is helping us to identify that pattern, right? So now in hidden layer there are circles. You can see these are called neurons or nodes, right? So we'll talk about these neurons in the upcoming slides as well. But the idea here is, if you see the architecture here, so there is an input layer. The data from input layer passes to the hidden layer, and then again the data from the output of the hidden layer goes to the last layer, which is called the output layer, right? So this is, you can see the sequence here. So this sequence is called the forward direction. So how do we get the prediction? We pass the data to input to the hidden layer. Input hidden layer data, like some functions we apply, detect the pattern, send the data back to the output layer. Output layer is nothing but the prediction that we get, right? So we have an actual value of y, suppose, and we have a predicted value of y through this forward process, and we take the difference, or we calculate the error. As simple as that, as we see in our logistic linear regression models or machine learning models, right? So now, how many layers we can add? We can add as many as we want to. Depends upon the complexity of the data that we have. Depends upon the problem statement that we are trying to solve. Left hand side we have one hidden layer and one output layer. Right hand side we have two hidden layers and one output layer. So how do we count, or how do we pronounce the topology of this neural network? Is very simple. The left side the architecture is called two layer neural network. Two layer means, although you see there are three layers, but input layer we don't count while determining the topology. So we start with the hidden layer. So first hidden layer and one output layer becomes two layer network. On the right hand side, simply we have two hidden layers and one output layer becomes a three layer neural network. Okay. So that is one thing. And then now the neurons. So what neurons is nothing but the output of the, so like you can say each circle here in each of the hidden layer is connected to the input data. This input data is nothing but your input features like x1, x2, x3, and so on and so forth. So here we have three input features. All of them are going to first neuron, suppose here, right? Which means all of them are connected to the first neuron. So which means is nothing but, if you remember the linear regression example, your y was equal to beta naught plus beta 1, x1, beta 2, x2, and so on and so forth. The same thing is happening here. Each node is equal to, suppose if we call it z, then is equal to w1, which is nothing but the parameter of suppose w1 is the parameter of x1 to this node. W2 is the parameter or the weights of this node to this input, and the third input, so on, so on and so forth. So there will be three weights like W1, W2, W3, or you can call it beta 1, beta 2, beta 3 as well. All of them are connected to this node. So each node generates one output. That output get passed to the output layer. You can see then this node, the first one, is connected to the output here. So here we have a multi-class problem. We are predicting two outputs. Here on the right hand side, we have three layers network, and we have a binary classification problem. Okay, so these are the nodes that we estimate. I have given the calculation here. You can talk about that. I mean, you can read about this later. But generally, now the question comes is people ask, okay, how many layers we can add? As I already mentioned, there is no limit to it, but depends upon the complexity of the data and type of the data also. Maybe like in a image data or text data, you can have multiple layers, right? So even 10, 20, 30, 40 layers. When you have a neural network with only one layer, right, that's called shallow neural network. When you keep on adding the layers, like more than one hidden layer is there, you call deep neural network. So that's the difference between shallow neural network and deep neural network. How many neurons you can add? Again, the same thing. You can add multiple hidden layers with multiple neurons. There is no limit to it. But again, as we keep on adding more and more data, you have to be cautious that it takes more and more time to compute, because you can see the architecture is pretty much complex, right? If you have like hundreds of dimensions here and 10 million suppose rows of data, your customer base, suppose the bank example that we are talking about here, if the bank has like 10 million customers, all of them are passing through neural network, then you can see how many neurons we need, how many hidden layers we need. So the computational power, the time that it processes takes longer and longer amount of time to complete one iteration or multiple iterations. So that we need to take care of. But apart from that, this is a one process of the neural network. So that's how the data goes through a neural network. So what are the weights and biases? Simply the parameters of the model, right? So you can say that like we are passing the input data here. So there are four inputs, and we are applying the activation function, the function here. Let's talk about the activation function later. But suppose y is equal to f of beta naught plus beta 1 x1 plus beta 2 x2, and so on and so forth. Now, if beta is linear, right? So which linear means, so if we remember the OLS, the linear regression model that we built, our y was equal to beta naught plus beta 1 x1, the same up to beta 4 x4, like that, right? So what do we mean by that? There is a linear relationship between y and x we are talking about. What do we mean by linear relationship? So if you remember, the interpretation of the linear regression is if we change the x by some amount, the proportional change in y is constant, right? Suppose beta value is 0.5. So we say that if x changes by 1 unit, there will be a 50% change in y. Okay, or x changes by 10 units, there'll be a 50% same thing, 50% change in y. So what do we mean by that? The proportional change in y due to change in x will be constant. That was the interpretation of the linear regression model, if you remember that, right? Which means that it'll always remain constant. The relationship between y and x will remain constant, right? So if you see this looks like a very similar to linear regression if f is nothing but a linear model that you have. If f of x is equal to simply w of t of x, w of t is nothing but it's a vector representation of your this computation. You can say beta 1 x1, beta 2 x2, and so on and so forth, right? So in Python, like mostly the data we take is in arrays, like especially in the deep learning libraries, the data is taken as arrays. And when we, and arrays and vectors, I would say, or when we multiply these, like when we write these to, this is nothing but a weight vector, and then we have x vector input data vector. If we are multiplying them, this is nothing but a matrix multiplication or vector multiplication, you can say. So it's a vectorization representation of your w and x is this equation, same. Okay, but what my idea here is that to tell you about the bias and weights, or uh, I mean parameters of the model. If this f is not linear, which means there is a non-linear relationship between x and y. Suppose it is a sigmoid relationship, logistic regression function. If you talk about, if you remember this function, 1 upon 1 1 plus e to the power minus z, right? So that is nothing but a logistic or sigmoid relationship between x and y, right? So that was if x and y relationship is non-linear. If it's a sigmoid relationship, then we have this function, this f is nothing but this equal to sigmoid function, or you can logit function, some people call it logit function also, right? So that's how the input and output related are. So now the question comes is like people ask is like how neural network is related to the linear regression. So again, the same thing. If you remember, linear to like we remember the traditional models were linear and logistic regression. Then we have machine learning models starting from decision trees, which is nothing but a partition algorithm. So there is no relationship between them. Whenever there is a non-linear relationship between y and x, we apply decision tree. Decision tree is nothing but partitioning your input data based on your y that we were doing. If you remember, the diagram is nothing but you have a data set, you take a split point, yes no, or true false, we divide a partition our data, right? So that kind of relationship is captured by a decision tree. Neural network has the capacity to identify non-linear patterns. So that's why there is a need of neural networks, right? There is a need of um, um, deep learning models, because always you might not find a linear relationship between y and x, because logistic and linear regression inherently assume that not only y is continuous, that is one criteria, but assume the relationship between y and x is linear. So that is whenever there is non-linear relationship between y and x, we tend towards like more advanced algorithm. Decision tree is one, which is based on partition, like boosting, bagging, all these are decision tree based algorithm. And then we have neural network, which has multiple of these type of functions which can identify the patterns. So that's why there is a need. It has plethora of activation, or these functions which can identify the patterns or relationship between x and y. So that's why there is a need of, from traditional algorithm to neural network to identify the complex patterns, identify the more nonlinear, more complex data that can be handled by deep learning models, neural networks, which could not be handled by decision trees or the traditional algorithms like logistic and linear regression. Okay, so these functions typically are called activation functions. That's a topology, again, terminology we use in neural networks. So this f is nothing but an activation function. So now you can see what is activation function. Typically, if we read about a definition, nothing but a gate, right? So you pass the input, you get some output. It's a function, right? So now gate can take you from top to bottom, from bottom to top. It can take you to the straight. It's a path, right? So the same thing is happening in the activation as well. You pass your data, apply the functions like y equal to f of x on that your data, and you get some output. That is what the gate is doing. That is what activation is doing, right? On the right hand side, if you see, I'm talking about linear activation function example that I'm giving. Suppose if you take a linear activation function here, and this is your equation, f of x equal to x. This is nothing but a linear activation function. This is a linear line, right? You can see, right? So if you take a derivative of this one, it equals to 1, right? So you got the derivative, right? So I'll talk about the challenges of the linear activation function. But why do we need to use an activation function? I've already spoken about that. If we don't use it, we end up building always a linear regression model, whether we apply even a neural network. But the idea is, because if you don't apply any nonlinear activation function, then you're applying a linear regression model. It's just that you're not using sklearn approach, you're using neural network model. Okay, so that's why there is a need to identify more complex patterns, more nonlinear patterns in the data. What are the types of, so we have seen here the linear activation example that we have an activation function. We can see the derivative is always constant, which means that beyond the point, if we want to update our algorithm, we want to improve the accuracy, we can't improve it because we'll stay here as constant. It'll be more clear as we move forward. So what are the other activation or the typical nonlinear activation functions available in neural network? There are multiple activation functions there in neural network, but we will be discussing of these four, and then you can use there are other activation functions are also available. You can have a look online later, right? So first is the sigmoid or logistic regression function, or logistic activation function, or you can say sigmoid activation function. This we have already seen in the previous slide, is nothing but a sigmoid relationship between y and x. So when do we use this? The question is, it's mostly used in output layer, right? So if you remember the output layer, if we have a binary classification problem here in this scenario, we were predicting either yes or no. Or if you remember logistic regression, we use sigmoid activation, right? So in fact, if we remove the hidden layer, right here, if we remove both the hidden layers from here, input and output, and if we apply the sigmoid function to these inputs, we are building a logistic regression model. Like as simple as that, right? So which means that sigmoid function is mostly used with the output layers whenever the output is required is 0 and 1, right? Or which means binary classification problem. Okay, there's another hyperbolic tangent activation function, which is nothing but Again, it's a binary classifier. It gives us the value between -1 and 1. This is mostly used in the image classification data, because that's why in the hidden layers we have a lot of image data that we pass, and we need the output between -1 to 1, or the range is -1 to 1. That's why we use it. Whenever we need the negative values as well in the output, tan h function is used. But most of the cases, both are the same thing. Okay. Third and the most used activation function is ReLU, or rectified linear unit. This is one of the mostly used activation function, but it is mostly used in the hidden layers, not the in the output layer. Why? Because if you see the function, how it works is it takes the maximum value of either 0 or the function itself, the activation output itself. So what do we mean by that? It can go up to infinity. So if you see the graph here, right? So below 0, it becomes 0, it becomes flat. And if it's greater than 0, it takes the value up to infinity. So if the range is 0 to infinity, you can say that, right? So most of the hidden layers are required. I mean, required an activation function, and we'll see the example also of this one in the Keras and TensorFlow. So we use the ReLU activation function. Again, there's a lot of maths involved in this one. I'm not going into the details of the mathematics, because then that needs a separate class, separate session to discuss all of these. The idea here is build the intuition, when to use what and why are we using that. These two questions I'm trying to answer. So please bear with me. In case if you need more mathematical explanation, I can definitely refer you to the articles which I have referred in the past, or you can also refer on your own. Right. The last one is the softmax or soft plus. You can say the algorithm, activation function that is used for multi-class classification problems. So softmax and sigmoid function are almost the same. It's just that in softmax you have a denominator like capturing all the probabilities. So if you have 10 classes, you have 1 upon like the probability of all the 10 classes. So that's the only difference, right? So you can also apply softmax on a binary classification problem, but we already have a sigmoid available. Then why do we need to use softmax, right? But mainly softmax is used whenever we are facing the multi-class classification problem. When we have more than one class, two classes, we apply softmax activation function. Okay. And there are each of the activation function have their own pros and cons. Like suppose if I talk about sigmoid and tangent function, right? So if you can see here, if we take a derivative, right? So we always, if you remember in logistic also, we take the derivative in the linear regression also, we used to take the derivative of the OLS function that we had. If we take a derivative of this function, the derivative is nothing but the slope, right? Or the gradient also people call it, becomes steep, becomes, horizontal as or on the edges, right? So if the edge start from here, you can see the slope of the gradient, or you can say this curved slope becomes flat, which means the value that the slope will take will be lower and lower as we move from this direction to this direction. So that's why what happens is the convergence of the algorithm becomes slower, because all the convergence depends upon the derivative of the function, right? So if the derivative becomes flat, the slope becomes flat, the algorithm convergence will also become slower. So if I relate this to the OLS function, the linear regression again, the ordinary least square, your function was y minus y hat, right? And what were you doing? You were taking the derivative of the OLS and getting the parameters beta 1 and beta 2, right? So if you, that is nothing but the slope of the OLS function. Now in linear, the slope was always constant, so there was not to like worry anything. But in logistic, if you remember, we were taking the slope of the sigmoid curve, and the slope was becoming flat after in the edges start. So what happens? The convergence takes time. How it creates a problem? There's a typical terminology people use it, that as the slope gets slower, the gradient vanishes, right? So of the or the slope vanishes. It's called the slope vanishing gradient descent problem, right? That we'll talk about later. It's a terminology I didn't want to use here. I wanted to use later, but that is a problem. When the slope gets lesser, the the gradient starts vanishing. That is a problem. That similarly, tan h also faces the same problem. ReLU also faces the same problem. You can see here after getting at 0, but ReLU has a fast process, because it, as soon as it goes to less than 0, it becomes everything becomes 0, right? So same thing is the softmax as well. You can see here also the slope is not like ReLU, it's not 0, it's slightly lesser than 0, you can see here. But again, the slope becomes the vanishes here. So all of these activation functions suffer from their vanishing gradient problem, or the slow convergence problem. To To overcome this problem, there are several other techniques are applied, or other functions have been used, like parametric ReLU, exponential ReLU. All these have been used. So, but mainly, even after doing the same problem, we have other techniques to handle these kind of problems. So that's why we use these functions mainly in our model, and then overcome the problems of these vanishing gradient problems. Okay, whenever we iterate once, we get some prediction, right? Because we have input layer, hidden layer, output. Hidden layer output goes to the output layer, apply activation function, get the prediction. The same way the other models work. So then after that, now so if we are lucky enough, our prediction can be as equal to our actual value, which is the target that we have, or it can be different. If it's different, we have an error. If it's exactly the same, we don't have an error, or we have zero error, you can say, right? But if we have an error, right, then what we do, very similar to the machine learning and boosting techniques. If you remember, we minimize the error, right? We try to keep our error as low as possible. Linear regression also, we do the same thing, right? So we want to, our OLS function is y minus y hat, so we always want to minimize the y minus y hat value, right? MSE, MAE, if you remember, the same technique or same loss functions, same errors we apply here as well. You must have heard this terminology in linear regression as well, but here as well, the same thing, the loss function. Loss function is nothing but the overall cost or overall error of the model. Like the first loss function is mean squared error. Similarly, mean absolute error as well available. Keras and TensorFlow, two deep learning libraries, we'll talk about those libraries as well, have already have inbuilt loss functions in them. So we don't have to worry about the loss functions much. But what are those loss functions? We have been already reading, so I'll not focus much on here. But typically, the loss function we use is whenever we have if you see this graph, I'm not sure whether it's visible or not, but the y is price here, which is a continuous variable here. And what you are doing is you are applying a mean squared error loss, which is nothing but y minus y hat, like on an average, how much error we are making in the prediction. That is what mean square error means, right? So as I mentioned here, for linear output, right, for a continuous output and non-linear relationship between x and y, so the loss function will remain same. So we try to minimize the mean squared error over the iterations in neural network whenever we have a problem of regression. Y is continuous. BCE, binary categorical entropy. This is the same as logistic regression output. If you remember the log loss, it's also called the log loss error, right? So if you, most of you would be familiar with this, minus y log of y hat minus one minus, y hat log of one minus y hat. It's the same thing. Uh, this is used as with sigmoid activation. Why? Because we have binary classification problem. So in output layer, we are applying sigmoid activation and we get y hat. We take the y hat, take the difference, like apply this loss function y on the binary classification problem, y minus y hat. We estimate the loss here. We calculate the loss, right? Linear, for linear, what activation function we apply? We don't have to. If it's a linear, we don't have to. But again, if it's a non-linear one, we have to apply non-linear activation function, even though y is continuous. So don't get confused by this linear regression. This is a linear problem where y is continuous, but the relationship between y and x is non-linear. That's why we need non-linear activation function like ReLU, sigmoid, tanh, all these ones. Okay. The last is the categorical cross entropy. Whenever we have multi-class classification problem, the same as binary classification, we have two classes to predict. In categorical cross entropy, we have multi-class classification problems. Like suppose we have an image data, we have 10 output like 0 to 9, right? We want to predict that. It's a multi-class problem. So for that, we need another loss category, which is called categorical cross entropy. The formula for here in this one, but the main thing is, how do we see that is in multi-class, mainly what we do is the output layer contains the same number of nodes equal to the classes. Like in binary one, if we had two outputs, we had one output node, right? This node is like neuron is one, right? Because we are predicting yes or no. For two classes, we have one node. For the categorical one, when we have multi-class classification problem, we need equal amount of nodes uh, as per the number of classes, right? So that's the architecture of the network, right? So these that's required by the model itself, right? So that we have to be very, very cautious when we are, because we need to enter the number of nodes. I'll show you how we apply that. We need to make sure that we are not making any mistake there, because if we do one less category, we'll be end up predicting less. That will not be end up predicting actually that's that category. Okay, that is the main thing. There is another one we will be hearing is sparse categorical entropy. Sparse categorical entropy, SCCE or CCE are the same thing. It's just that how you define your input data. It's just that you have to change your input data. In categorical cross entropy, Y is entered as a one hot encoded vector, because some multi-class we have 10 classes, so it becomes a whole matrix. And in sparse categorical cross entropy, Y is passed as it is. Automatically, the algorithm takes care of the class of Y. So we don't have to worry about that, which means automatically the parameter converts into one hot encoded vectors and calculates our loss. That is the loss function. Okay. Uh, so so now after calculating the loss, and there are multiple couple of other losses you might also hear, but all of the idea is the same. We are actually either predicting a multi-class classification problem, or it's a regression problem. It's a supervised learning algorithm, so we have typical set of loss functions available with us, which we use in the algorithm. Okay, so don't worry about the theory part. If it's you miss this something, like it's easily available, it's a very simple content that's available online. And as well as we will be, once we start the application part, I'll go through one basic set of keras, like how we build a neural network on a MNIST data, and then we'll move to the application. So that's why we kept this technical section, so that everybody can understand, at least even if we miss the theory a bit, we can understand from the application. Okay. So now this part till here, we calculate the loss are fast or forward propagation, or you call it forward direction process ends. Like one step we have completed. We have come from input layer till output layer, calculating the loss. We have completed one forward step, or some people call it it's as a forward propagation. So we have come into so we have completed a forward propagation process. Right now, let me again go back to the linear regression part. If you remember the OLS, the ordinary least square method, that was the algorithm that we were using in linear regression. We were trying to minimize y minus y hat, right? Total sum of y minus y hat square. So there, um, what we were doing is we had an equation y equal to beta naught plus beta 1 x1, beta 2 x2, and so on and so forth. We were predicting the y hat, taking the y minus y hat. That was a OLS function. And that OLS function, we were optimizing it, right? How we were optimizing it? We were optimizing it by taking the derivative of OLS with respect to all the parameters. What are those parameters? Beta 1, beta 2, and so on, right? So we were doing that in the OLS method. So there was no no forward propagation or backward propagation kind of process, right? It was simple optimization problem we were solving, right? But in neural network, the architecture is different. So this is also, we are minimizing the loss, because OLS is also a loss. Y minus y hat is nothing but the cost from the model. But we were solving the loss, we were minimizing the loss in a different way. Here we are minimizing the loss in a different way. Here in neural network, we minimize the loss not via OLS, but by using a back propagation process and using some specific algorithms in the back propagation. Okay. Now, what is back propagation? Again, overall, back propagation is an iterative process, like you can say, in which what we do is we minimize our objective function, okay, um, via updating the parameters. The parameters we have are nothing but the weights and biases, right? You can see here that x1 and x2 are the two features that are passing here. We are applying activation function here. We're calculating the y hat. After calculating the y hat, we calculate our loss. So that's a forward propagation process. Now what we do is we go back, we take this L, we try to minimize this L over the number of iterations. We run multiple iterations here. How do we do that? We take the derivative, which we also did in OLS, like d of L by dz. Dz is nothing but the activation. After applying the activation, our output, the simple, this one here, right? How do we do that? So again, it's a mathematical concept, but to tell you intuitively, what we are trying to do is we are minimizing this loss based on the unknown parameters of this equation we have. And what are those unknown parameters? Are W and B both. W is the weight, B is the bias, right? So you can see here, I am trying to this loss derivative I'm taking in the first iteration. Like suppose I take the first iteration, first back propagation iteration, I do calculate it one time. I'll show you example as well. How do we do that? Then second time again do that. What I do is I minimize, I take the derivative, get some weights and biases value, get again calculate my prediction, then again calculate the loss in the second iteration. And if I see if the loss is still high, I do the same thing again. Again, I pick up the loss, whatever loss from the last time I pick up, minimize that, take the derivative of the same loss with respect to the parameters, and calculate the um, again the weights and biases. Same thing we do it iteratively. What are we doing is iteration equal to 1, right? So there is some weight and some bias and some cost is given. Now from from the start, where do we get this weight and bias? Like from iteration 1, we did not calculate any. And if you see here in the till here, I have not told any process of calculating the weights and biases, right? So from where this weight and bias come from? Ideally, the process is we take it randomly, we choose it randomly, or it's called weight initialization process. So if you remember the k means algorithm, right? So we initialize the k, right, from some like random, randomly we initialize the data points as the centroids. The same thing we are doing here. We are randomly initializing weights and biases. How do we do that? Or there is another debate that is going on in deep learning, that how do we make this process a little better? Because what can happen is, if you choose weights and biases too randomly, it can impact your accuracy. It can also impact your number of iterations of the model, because if you choose the weights and bias little away from the realist, I mean, you can say reality, it might take algorithm forever to converge, right? The same process is that it can either, I mean, we are looking for convergence here, but because of the randomization, it cannot converge ever, right? Or we may end up using, I mean, losing or having less accuracy, you can say. But that is a different process. We don't get into that part. But what I'm saying is, in iteration 1, we start the weights and biases with with a random value. Some people start with 0 as well, but randomization is better than 0. Over the period of time, people have realized this one. But what are we doing here? In the first iteration, now let's go to the graph here, this one. In this picture, if you see, there is a line that we are trying to fit on the data that we have. The blue dots that we have is the data. The line that we have is the linear line that we're trying to fit. It's easier to visualize. That's why we're taking linear examples more. But you can see we are here. Now, if we calculate the loss, what will be the loss here? Loss will be very high, right? That is nothing but the cost here, 197.25. That's some number. Assume it's given to us from outside. So you can see the difference, right? So we calculate the total loss. The total loss of this process is 197.25, right? Now, suppose we say, okay, no, this loss is very high. What do? We take more iterations. Now, from 1 to 10 iteration, we add more 9 more iteration in this model, and you can say we are updating the weights from 0.28. Now, from 0.0 dot 0.032, we have reached to 0.28, which means we have increased 0.25 points of the weights and the bias as well. And we have, you can see the cost, significantly reduction in the cost, 197 to 74, which is this. So now we are saying, as we increase the iterations, we are trying to like our model, our line is fitting the fitting better on the data that is available to us, right? Same thing, we do it again. We add more iterations. We reach more optimal points, and we keep doing it until we reach here, which is, suppose 30, after 30 iterations, we have some weight, some bias, and then we have some cost, which is like 43 something here it's mentioned. But you can see here how this cost is decreasing. From 197 we started from, we are reaching, we reached at 43. Can it be reduced more? Most likely yes, from 1 or 2 points. But you can see, as we increase the number of iterations, the cost curve that is going down is becoming flatter and flatter, right? Which means that after a point of time, the loss will not reduce, right? So that's called the optimal point. Exactly the same way the gradient boosting, if you remember, that works. Same way it's working. Now, this is one part of it. This is how visually it looks like, which we saw here, like this process, like one iteration and then second iteration, third iteration, so on and so forth. Now, how this the whole thing is working, how we are getting the, like how we are updating these weights, like we add more iteration, then how the weights are getting updated, that's another question people ask, right? And this is a typical question of the or the back propagation part. Now, this back propagation is totally dependent on gradient descent algorithm, right? That's what, like, I wanted to. So this is a back propagation process. The whole step that we are talking about, we use gradient descent algorithm to minimize the loss function. So the objective function of the gradient descent algorithm is nothing but to minimize the loss function that we calculated, right? The cost minimized. So gradient descent will always have to have a function which it wants to minimize, right? So that function we want to minimize the loss function, right? Now, suppose a loss function looks like this, a U curve. So what do I mean by say this? If you remember, a parabola is y equal to x square. So we have a parabola here as well, y minus y hat square. Suppose we talk about MSE, or the categorical binary categorical cross entropy is also plotted like this. It's a convex curve, shape of the loss function that we have. Why do we have a convex curve? Because we want to find the minima of the loss function, right? And convex shaped curves always have one minima. That's a mathematical, terminology. So which means that this is the minima, right? This is where we are reaching the minimum of the loss function. If we go, to the right of this function, we'll be increasing the loss, which we don't want. If we go left to the to this point, we'll again be a loss will be higher, which we also don't want, right? So we want to settle at this point, right? Now the point is that from where do we start and how do we proceed. So there are two things here. Where do we start from, which direction we should start from. The second is, or which direction we should move. The second is what magnitude we should move. Two things we need to answer. Gradient descent algorithm are like, in the by using the gradient descent algorithm, we tell that okay, this is the direction and this much is the magnitude we should use to reach to the minimum of the loss function, right? Okay. So what I'll do is, if you see here, this is the parameter and this is the loss function, the value, the loss that we have, right? The same thing, the cost here. So and this you can see clearly related, right? So if you keep increasing the iteration, it will start making a U-shaped curve again, right? So what are we doing is, with the random weights, and in the x-axis we have weights here. We are minimizing the loss with respect to weights and unknown parameters, weights and bias. Like suppose we talk about weights here first, the W. Okay, so with the random initialization, suppose we are here, we have a very high loss. We have a W value which is here somewhere, and we have a very high loss, which is suppose the point that we are talking about here, right? Now how do we, now here we can move two directions, we can move into two directions. One is further going upward, right? But that doesn't solve our problem, because if we go upward, we are increasing the loss, right? Ultimately we want to minimize the loss. Or we can move downwards. That's a directional part, which direction we should move, right? The second is how much we should move, whether we should take, one step and then reaching from here to here, or we should come slowly or faster, depends upon the, again, where we are. And and there are certain parameters which help us to reach to this minimum point. So if you have studied about gradient descent algorithm, it's very intuitively it does make sense that the direction that we want to move is the negative of the slope. Is the, I mean, the relation of the direction that we want to move to minimize the loss is actually the negative of the slope of the function, which means that here, if you see, the slope of the loss function, which is dl by dw, is negative, right? Which means how do we want to proceed in this direction, which means we want to increase the w value, right, to minimize the loss. On the other hand, if we are here, we have a positive slope, which means that dl by dw is the derivative of the loss function with respect to w is positive, which means that we have this direction. To minimize the loss, we have to move from right to left, right? So in this direction to reach to the minimum point. Okay, so which means if the slope is positive of the loss function with respect to the parameter, then we have to reduce the current the I mean we have to reduce the weight size to reach to the minimum point. If the slope is negative, then we have to increase the weight size to reach to the minimum point. That's the rule. So that direction we got it, right? So this is what the direction is. So with the slope we get the direction. Now how much we should move, again the slope only tells, right? Okay, so so how, and sorry, yeah. So that's the direction we got it. Now how much we should move, or what should be the magnitude of the movement, that is also told by the this. There is a rule that is proven mathematically. Again, it's called delta rule or update rule, right? So what you do is, you take your new parameter, which is the weight parameter, new parameter is equal to your old parameter, which is the existing parameter, wherever you have calculated the slope, right? Plus some step you have to take. That's a magnitude, right? So now the question is that what step or how much we should take. That is told by this, expression here. So this is nothing but the slope, the dl by dw, which we calculated in the previous slide, and the learning rate. This is called learning rate, or lambda, or alpha, some people also call it. So don't go by the terminology here. But what you're saying, you're saying w new should be equal to w of old, the existing parameter, minus the lambda of multiplied by the dl by dw, the slope of the parameter, slope of the loss function, right? So that's what we do. Now the point is that how much we should move is again the question. So one is slope size. Learning rate is helping us to control the slope, the size of the step that we are going to take. How? Learning rate is always a number between 0 and 1. Now slope can be any number, right? Now what, imagine a very simple, that if you take a large slope, very high slope, and you start taking the steps in this direction, by only depending on the value of slope, you might take larger steps and you overshoot your minimum point. To control that, we multiply this slope with a parameter called lambda or alpha, which is always between 0 and 1, to control the rate. Imagine that you are playing golf, right? So you have a direction that you want to put the ball on the hole, and the point is that how, direction, that this direction you have to go, but how far you should go. As you get closer and closer to the main goal point, right? So you get your speed slower, because you can't play a full shot, because then ball will not reach to the goal point, it will cross the goal point. The same thing is happening here as well. To control your speed of the slope, we have to multiply this learning rate, right? So that's where the learning rate is useful for. It is a part of gradient descent algorithm. We'll see how learning rate gets applied in Keras and TensorFlow, but that's the intuitive interpretation of the learning rate, right? Same thing is happening here. Like, you might have a function like this again, but it's the same thing. If you're here, you have to move in this direction, which is a negative slope. Here is a positive slope. You have to move in this direction. Same thing here, negative slope. You have to move in this direction. Otherwise, this direction. Like, if you're here, you have to move in the left direction. So that's the whole point. So you might have a complex, kind of loss function, not always be. So here, okay, if you have a loss function which has only one minimum point, it's called a global minima, right? It's called global minima, global maxima. You can, if you invert this shape, the inverted U, it'll be a global maxima. Typically, if a convex shaped curve has one global minima and global maxima points. But if you have a curve like this, where you can have two minima, right? So wherever the minima is lesser, it's called local minima, and wherever the minima is a deeper point, it's called global minima of the function. So for the whole function, this is the global minima and this is the local minima. We'll not talk about the challenges, but if what can happen is, if your loss function is like this thing, and you start the gradient descent somewhere here, suppose random initialization, you might end up reaching here and you never come out of this one, because, but that's you I mean you if you reach here, that's not your minimum point. That's the minimum point is of this function is this one. So how do you come there? There are certain techniques available, but this is also a problem in a function. If you have a flat, if you have a curve like this which has multiple minimum options, you might never reach to the global minima. So this is one of the challenge that people face when they apply on the gradient descent algorithm on a large data or a complex data set. But we'll not talk about that. That's not the agenda here, but that's the gradient descent works. So how the gradient descent work, as I told you, overall, like, you are from iteratively, you're trying to minimize the loss function, updating the weights and biases, right? That's what the gradient descent is helping. And that's by using the gradient descent algorithm, your back propagation steps or process gets complete. How do we build a neural network, a deep learning model in Keras and TensorFlow libraries? I wanted to talk about that, right? So far, I think we have learned the sklearn library, where we have MLP or classifier as multi-level layer perceptron, a model that we have built there. So Keras and TensorFlow are the two. In fact, TensorFlow is the one of the library mostly used, built by Google to develop deep learning algorithms, right? It helps the data scientists to build deep learning algorithms. And Keras is nothing but inbuilt API or system or another library, you can say, which is directly helping us, where we download the components of, like, the way sklearn works, the same way Keras works. So we download certain, models which we want to build, like the way we do it in sklearn. You can simply compare both of them, and especially is dedicated more towards deep learning models to like artificial neural network is one which is mostly used for tabular data. Then we have image data, CNN. Then we have text data, or the sequence data, where the RNN fits the more. So all of these models can be built in Keras. Okay. So we are using Google Colab here. I am assuming, because last session also we covered that, so all of you are aware of how to use Google Colab. So I'm not going into the details of the Google Colab, but the environment here we are using is because we can't run it like on the local, unless and until we have a very like, I don't have a system which runs the Keras on my local. It's a firewall blockage, so I can't download that. So that's why I have used Google Colab. But if you have local machine which can do that, definitely you should try doing the local machine as well. But what are we trying is, if you remember the architecture of neural network, we have a sequential process, right? First we go forward direction, and then we come backward direction. So it's a sequence kind of process, because we are building model in neural network in sequence, right? So the same thing we follow here as well. The Keras architecture is also same. We work in layers or sequences. That's why we download the class called sequential class. Okay. So what do we do is there is a data set, inbuilt data set in Keras, very famous. Everyone uses the MNIST data set. It's a handwritten image data set. Again, it's a multi-class problem. You have 10 classes from 0 to 9 and 28 by 28 pixel, which means the dimension of the data, right? Although it's a grayscale images, but it has like multi-dimensional data, right? So how do we download the data? There is inbuilt class here, MNIST class. We download the data from there, load data package, xtrain, ytrain, xtest, ytest. I have downloaded here. There are 70,000 images, 60,000 plus 10,000 test data we have. And here in this process, I'm normalizing it or scaling it, you can say. Now the point is, question comes is, do we need always, like for the neural networks, do we need to scale the data? Not mandatory, as we do in the same linear regression process. But again, because we are applying gradient descent algorithms, back propagation, you can see the convergence is always better, faster, smoother if we apply scale, if we scale our data. Okay. If we don't do that, it will converge, but it will not impact your accuracy, right? But if you have large data set, it's better to normalize, scale the data, and then pass it to the hidden layer, the input data I'm talking about. So that's why we are doing the same here. We are actually so it's nothing but the value minus min divided by max minus min. There are the data rise, like so pixel data actually, I'll show you how the data gets stored, but the value is from 0 to 255. So the pixel values are given. We are scaling the pixel value between 0 to 1, right? So you can see here, this is the data, how it looks like. The 7 number that I'm printing, the first data point of the X train, or if we see in terms of array how it is saved. So you can see here how it is being saved, right? The array form. So all of them are 0, 0, 0. I think from 8th or 9th row, the data starts like this. You can see, read the numbers. So that's how the image data gets read. Same thing in the color image also happens, right? The data, you can see how the numbers are getting read. So the 28 by 28 means 0 to 27 rows. It's a matrix form data, 0 to 27, which means 28 by 28 pixels of data that we have, right? So this is the actual training value, which is 7 y train. And how do we define a Keras model? Again, the same thing. The model expects input dimension 28 by 28 argument, which is the multi-dimension data that we have. So we form the model in a sequence way. Keras define a sequence of layers, right? So what we call it, tf.keras.models.sequential, that we class that we called out, and then we keep on adding the layers. Now, how many layers we are adding? First is the input layer. So input layer we have to pass. One thing is we have to pass the input shape, which is 28 by 28. That's a data shape that we have. That will do it in a Tableau data as well. Then we start adding the hidden layer from here, right? How do we add that? We call the class called model dot add tf.keras.layers dot dense. Now, what do we mean by dense? Dense means that each of your layer is fully connected to each other, right? So if you remember the image that we started with, the architecture, so you have here like 3 inputs here and 4 nodes here. The 4 by 3 is 12 combinations, right? So you have, which means that each of the node is connected to the previous, fully, like all the nodes of the previous layer, right? You can see here each of the nodes here in the hidden layer is fully connected to the previous layer. Similarly, here as well, both the nodes are fully connected to the previous layer. So whenever there's a full connection between the layers or between the neurons, it's called dense layer. Okay. So so we are defining a dense layer here, which means that the layers are fully connected, which means the first hidden layer is fully connected to the input layer, right? Okay. So 300 neurons, again, as I told you, that there is no hard and fast rule how many neurons we need to add, but 300 we are passing here. Activation equal to relu. So this is the activation function which we need to use. I told you you can use here other activation function as well, but relu works relatively faster. That's why we use relu, and it's mostly practice technique to use relu. Whatever data we have, even people use relu in the image data as well. It works better. I mean, faster and better, you can say. Okay, so then 300 neurons we are adding in the first hidden layer, 100 neurons we are adding in the second hidden layer. So then we have 2 hidden layer we are talking about here. And then how do we know this one is the output layer? By looking at the this neurons as well as the activation function. So because we have multi-class, our activation function is softmax. Dense because fully connected to the previous layer. 10 means we have 0 to 9 classes to predict. Okay, so that's how now this is the architecture of the neural network. You can say model dot layers. You can say that you can see the layers. Like first is the input layer, which is flattened, means that you are actually converting the column data into row form, like 28 by 28, 784 values you're passing as a row in the data. Okay, model dot summary, you can type number of parameters, right? So number of parameter, how can you calculate? 28 by 28, you have a shape of data 784. Your first layer has 300 neurons, so 784 multiplied by 300 plus 300 is equal to bias term, because we need bias as well, right? So w of x plus b, that's the first thing we are adding here. Same thing, 300 by 100, which is the output of the first hidden layer to the second hidden layer, 100, 300 by 100 plus 100 is the bias term. And then we have 100 by 10, which is the output layer and the hidden layer per connection, plus 10 is the output, which means that total, if we add this, it becomes 266K parameters. Now you can imagine that if you have large data, this is only a 70,000 images. You have millions of images, you have millions of text data. How many parameters will be there to train, right? And all of these parameters will be updated, trained, right? The w, these are nothing but w and b, which means that these many parameters we have to update. Can logistic and simple model can handle this? Difficult, right? So that's why we need these kind of deep learning models to run uh, the complex data problems or large data problems, right? You can also get the hidden layers and the weights. I have not going into the detail ones of this one, but just I want to show you the how to then put, the next step is basically after defining your keras model, which you have done that in the past, you compile the model. There is a compilation process. Loss function, if you remember, categorical cross entropy, binary cross entropy, MSE. We are using sparse categorical entropy. I told you sparse is that you have multi-class problem, so you don't have to one-hot encode the data. You just pass as it is the data. That's the only difference between categorical one and sparse one. But optimizes stochastic gradient descent. Now, gradient, this is nothing but the type of gradient descent. There are multiple types of gradient descent: stochastic, mini batch, um, there's another one, the batch gradient descent, which is the same thing, right? So stochastic gradient descent is technically what it takes, it takes one row of data and pass it to the model. So one by one, like it passed the data to the neural network and gets the output. So you can imagine, you can imagine that with a normal gradient descent, which is called batch gradient descent, the whole data is passed to the neural network. In stochastic gradient descent, one by one the data is passed. That's the difference. And batch gradient, mini batch gradient descent means small batch of data is passed, right? So again, SGT might take more time, but it's easier to, computational power is lesser, because instead of passing the full data, you're passing row by row data. Okay, you can read about them. These are pretty simple, like definitions we can avail. This available. I mean, available online as well. Then we call the class that we created model.compile loss equal to loss function. This one, you can also put the name here, optimizer and metrics. Now you can pretty much easily see that these are nothing but the hyperparameters of the model, right? So like you can say loss function and optimizer are typical two hyperparameters of the model. You can change the optimizer, whether you can get better accuracy or not, you can validate that. Loss function, you can change that, like categorical cross entropy, you can change that, but most of them the same thing. But optimizer is one of the main hyperparameter we'll be using. Um, um, so then, yeah, I'm just checking the shape here below. So after compiling the model, I'm checking the shape, and then you fit your keras model. How do you fit that? You have a validation data set, and I'm creating a class called history to capture the history of the, like, each of the output. Model.fit train. Now epochs is nothing but number of times we want to pass the whole training data into the model. Like suppose you have 100 examples or 100 rows of data. One epoch means that the whole 100 data points will be trained from the model, right? 10 epochs means 10 times or all 100 records will be trained by the model. So which means we want to run that 10 times the process, right? Validation data is the same validation data here. Batch size is now, if there are multiple, I mean, if there are many records in the data that we have, then it's, instead of passing the whole data in, like, in the model, we pass the data in batches, right? Suppose we have, as I told you, that 100 examples of data. So one epoch will be the whole 100 data points will be passed to the model, trained, and we'll get some accuracy. In the batch size, if we define batch size equal to 10, which means it'll take 10 iteration to complete one epoch, to complete the whole 100 data points. So which means that 10 times it'll run one by one, like first 10 records it'll pick, then next 10 records, and then so on and so forth. 10 times, after running 10 iteration, it will complete one epoch. The same thing is happening here as well. We have 55,000 observation in the trained data, and we are running 10 epochs with a batch size of 32. By default, the batch size in keras, by default, the batch size is 32 only. So you can see the calculate. Like if you divide 55,000 by 32 batch size, you will get 1719, which is the one, like each the number of iteration or it'll take to complete one epoch. So you take 17, 19 iteration to complete one epoch. Similarly, we have to run this model 10 times because we are passing 10 times the epoch size and get some accuracy. You can see that the training accuracy we're getting is 97%, and validation accuracy we're getting 96, 97%. The same, almost same accuracy we can say, right? So the model and is good so far. Like we are getting good, decent accuracy. And how do we save the model? It's very like I'm creating a function here. There is a um, I mean, you can create this the same function here and directory, and then you give the path to save the model. So this is I am saving in my local drive. You can also follow the same thing, right? So that is how we do the model. And yes, if we store the history, you can see you can create a plot that how our model is actually improving or reducing the loss and improving the accuracy over the iterations, right? Okay, how do we do the predictions? Model dot predict, same thing. This is the confusion matrix. We have multi-class problem. You can see the confusion matrix. You can for each of the class, you can see the precision and recall and F1 score, right? The same way we call the confusion matrix. I am not doing different. It's exactly the same way. Classification matrix and classification report in confusion matrix. And we have predictions, model dot predict on the new data. So new data is nothing but, suppose 4 records I'm taking from the test data here. You can see that how it is predicting. Or to show it visually, I can just show you that here the actual was 7, the data model predicted is also 7, right? Here also, like actual is 2, the model predicted is 2, and same thing is here as well. Actual is 1, model also predicted 1, right? Same. So this is how the model is built in Keras, right? So the TensorFlow model that we have now, we have like here till here we're able to predict, or we are able to build a neural network, a deep learning model by using Keras and TensorFlow libraries. The banks now able to, because of their capacity, technical capacity has also increased, and there's a they have like a large data set to handle. Like so they need now machine learning and traditional models only, like only using traditional models and machine learning models won't be that much helpful. We need to use certain advanced technique to get the to create a system which will identify the default of defaulters or default of customers or fraudulent transactions. You can increase the scale the problem. Like credit is one area, is one domain, and where you have risk, you have fraud, you have other things, right? So you can apply all these business domain, like all these technique, that the technique that we have seen in all these domains, right? So that is one thing. The target variable we are talking about here is a class of event, whether the person will actually default or not default, or you can say credit worthy or not worthy. uh, Defining defaulters, yes, individuals who have a bad credit history in the past. Time period, we have not. So we are taking the data from like a slightly modified data, so we don't have a time period specifically available, but it depends upon time period, like what performance window and observation window we talk about. Analyze population, we have a sample data set of 1,000 individuals, or the bank data set. Modeling technique, again we'll try here artificial neural network or deep learning algorithm. What is a validation window, which means how do we want to um, what data set we have for the prediction. We have a validation data set available from the data set itself. The model framework, typically because machine learning, deep learning is part of machine learning itself, the model framework remains the same. You basically you get your data, treat your data, whatever EDA you have to do, feature engineering, reduction techniques, what you apply, model building part, model validation part, and implementation part. Right? All the processes, the cycle remain the same because deep learning is part of the machine learning. It's just that it's more technical in terms of component wise, and it is a little more resource heavy, you can say. We have a credit data set. Again, we are now we have a tabular form of data. So that one, the example that we saw was image data, multi-class problem. Here we have binary classification problem where we have two classes, 0 and 1. We need to predict whether the individual will default or not default. Okay, how the data looks like, to show you, like this is the data that we have. So I'm not explaining the data in detail, and also not I'm covering the EDA part here because I left it to you guys. You can do it because that we already have been doing so far, so many times. So that's why, but I wanted to focus more on the architecture and technical components part. So that's why I'm not covering EDA here, because the data is clean from my side. I've done that in the past and then using the clean data. But again, if you want to apply this, you can apply post the I'll go if you want to run the model here, but do the EDA part on your own. Okay. So yeah, the data set we have is credit data, and we have around 1,000 observations with 21 columns. Last column is actually the class column, which we want to predict here. So there are a couple of, again, numerical features and categorical features as we see in the tabular form of data. So yeah, so then we see the class distribution. We have 70% of zeros and 30% of one, which is pretty much fine. Like we don't have to worry about the skewed distribution. Like 30-70-30 ratio is okay, acceptable in the industry. So but in terms of credit industry, it's heavy. It's little heavy because data is modified. Generally we find 5 to 10% of the defaulter, even lesser than that. So defaulter rate cannot be more than 5% because then it'll be a huge cost to the bank, right? So info on the data set, yes, we have certain features. Couple of them are numerical or object type. So that is available. Credit data missing value, again, as I told you, we have treated this data, so there is no missing value in this data. So I'm not worried about the missing value part here. No EDA part is covered. But you can see here, then what we do is that, yeah, the credit data, and then why, yeah, let me start with the encoding part, which is the one hot encoding. So we have a couple of numerical and categorical features. Now let's start the data pre-processing part. Get ready, like get ourselves ready with for the model. Like neural network also take the same way, right? So it cannot take the text. We have to convert the string values or text value into numbers so that we can pass the model, pass the data into the model. How do we do that? We typically apply the get dummies or PD one hot encoding technique. You can say here, what I'm doing is I'm calling the, so first I'm capturing the categorical columns from the model, select type object, all the categorical column into a list. And then I'm selecting that categorical, creating as a categorical data by taking all the categorical columns from my credit main data set. Okay. So which is these columns: status of existing checking account, credit history, purpose, foreign worker, and all these. You can see these are all categories. Some of them are bureau data, so we have data. We should have ideally data dictionary for this one. I'm not covering that, but all of them categories have some meaning in themselves. Okay. uh, then we apply get dummies on the categorical data that we have. So then we have from 13 features of the categorical one, we've reached to 54 features, right? So like we after applying the one hot encoding technique, right? So we have credit data encoded. Then what I'm doing is I'm taking my categorical data and dropping all the categorical columns from my main data set and combining one data. So which basically means that I'm preparing my data with all the columns, numerical and categorical, into one data form. So I have done that here. Credit data encoded has encoded features, categorical features, as well as numerical data here. From here onwards, you can see, right, from the credit amount or duration in month amount, duration in month and credit amount, right? So that's a numerical column. So I've combined them. Now what I do is now I do train test split. So how do I do train test split? Simple. There's one technique I want to capture here, and I think we miss that most of the time, but some people do it. People who do it are good. People who don't do it, please take care of this one. What we are doing here is we do train test split on my credit main data. Okay. So and simply the code we apply is the train size we take, like we define a data, like we call the function train test split. We pass the data, our train size, the data set that we want to keep in the train data set, 70-30% ratio, and random state. What happens is you can see now that after creating this, I'm creating df train, df test, df y train, df y test. So you can see the distribution here. If you remember the previous distribution, the distribution was 70-30, right? 70% and 30%. Now, after changing after creating the train and split, the distribution changes. My train data becomes 71%, 28%. My test data reduces to 69 to 30%, right? So there's a distributional change, right? So it's happening. And if we have multi-class problem, here it is not visible that much. If we have multi-class problem or if we have skewed distribution, this distribution difference can be even bigger, right? You might have a test data set which might not be representative, right? Because you have a distributional change. What if you have 5% ones in your overall data? After doing the train test split, you are left with, in the train data, you have 10%, you are there with the 10% 0 1 0 to 10 ratio of the 0 and 1s, and in the test data you have only 2%. So that is also possible. So in the skewed classes, it can also be even severe, but we need to be careful for that. To do that, there is a simple technique we do is stratified sampling. So we must have heard about this in stats classes. So what we do is we stratified equal to y, and then what we do is we can see that we compare the distribution in the train and test. We make sure that our test and train are both on the same distribution. Okay. Actual data in future can be different. That's a different scenario. But the idea of the train and test is that they should be the distributionally equal. Okay. So then after doing that, so then I'm this is my train data and this is my test data. Now I'm doing the scaling part. Again, we do one more. Sometime we miss here is that we do the scaling on overall data, right? We scale overall our main data set, and then we then do with train and test split. So if you see here, we have done the train and test split first, and then doing the scaling part, right? How do we do that? We first extract the numerical columns, and what we do is we on our training data, which is we're creating training numerical data. I'm from my dfx train, I'm extracting all the numerical columns, and I am fitting a min max scalar um, um, process on my train data only. So I'm doing fit transform on my train data, right? Just take care of this one. Some people do it in overall data. Don't do that, because then what happens is it is storing the mean and standard deviation, whatever the, like here we have minimum and maximum value from the train data itself, because that's what we are training our model. We don't want to train, we don't want to fit transform on our test data, right? Or we only want to transform our test data, so that whatever the data that we have test data in, I mean, in our test data should be not visible to the, I mean, model should not know about anything about our test data, right? That is the whole purpose. So that's why we only do transform on the test and fit transform on the train part. So that's why we had to do like first train and test split, and then apply these techniques here. So I'm train data fit transform, you can say, and test data I'm doing the transformation part. Okay, so you can see here transform part, so that my whatever parameters that I've created, the my min max scalar is creating, that should be saved from the train data, should be applied to all the data which the model has not seen, which is one test data here, as well as some future data set. Okay. Okay, so then as I told you, as I told you, that the model, the neural network deep learning model takes the data into array shape, as we have seen in the image example, right? It has to, the data has to be passed as an array. So then what we do is from the training and test, we create arrays of the data, right? So which means it data looks like that. So how do you see, like if I see train data first observation, we had 704, observations with 61 columns. But if after converting the array, how do the test data look? How do the X train looks like? It looks like this. You can say there will be 61 columns. It will be one row. Similarly, Y test or Y train, how it will look like? You can see that this is also an array form, right? You can say the 5 observations I'm seeing, 5 classes I'm seeing. It's a binary classification. So this belongs to one, like whole data is this one, and then this one class, and then second, third, fourth, and fifth. Okay. Yeah, you can see type here, which is numpy array. Now the same process follow, define and compile Keras model. How do we define the model? I've created a function here, but the process is same. You can see layer one, which is the the first hidden layer. We first call model sequential, and that in the model sequential we are adding the layer. um, 10 neurons we are passing, right? We are not passing 100 200 here. It's a small data set, we are passing 10 neurons. Again, it's subjective how much we want to pass. Looks like it's a small data set, we don't have very complex problems in this data, so we can pass less number of neurons. You can try with other values of neurons. Input shape, input dimension, the same way we entered the input shape 28 by 28, here also we are adding the input dimension. Input dimension I've taken, must have taken here, which is nothing but the value that we want to pass. Input dimension, how many columns we have. So we have 61 columns here. We'll enter 61 later, right? So then activation equal to relu. So we are adding relu activation here in the layer, in the first layer. Then we have second layer, same thing. Model dot add dense, again 10 neurons, and then activation layer is relu. Activation function is relu. Third layer. So we are building 3-layer neural, in fact 4-layer neural network. You can, no, sorry, 3-layer neural network, because the third layer is output, that is sigmoid activation, right? So we need binary output 0 on 1. So that's why we need one node, right? And the sigmoid activation function. Okay, optimizer, there we were using SGD, stochastic gradient descent. There is another algorithm called adaptive moment optimization. It's a mix of little advanced technique in the gradient descent algorithm. You can use that. Right now we have not discussed this, so you don't have to worry about that part. You can use same SGD as well, but this Adam is one of the other optimized algorithm uh, on the gradient descent algorithm that we pass with a certain learning rate. As I told you that gradient descent takes learning rate, so we have passed 0.01 learning rate. Okay, people now can question, okay, how much learning we should start with. The idea is in the industry, wherever, whichever model it is, whether it's a, even it's a gradient descent or gradient boosting algorithm, or it's a neural network algorithm, we start with a low learning rate, and then over the time improve the learning rate. Okay, sorry, high learning rate and then reduce it. I'm doing the reverse way, sorry. Um, then we here we are just printing the model summary, and then we are compiling the model. So I am defining and compiling the model in one function. You can also follow the same process. Binary cross entropy, why? Because we have two classes. Binary class we're predicting, optimizer the same, SGD or Adam, and then metrics equal to accuracy we are interested in. So we are passing as a parameter here. So if we are interested in F1 score, precision recall, we can put that as well. Okay. So then we return the model, right? That's a function that we built. How do we fit the model? Again, input dimension, we know that we have 61 columns. So we pass the 61 features. Here, training epochs, 50 times we want to pass the whole training data set, right? So batch size, the same thing. Metrics equal to accuracy. Validation set is nothing but the validation set X test and Y test that we have. How do we call the model? I'm calling the DNN binary classification KS here, right? Input dimension 61, matrix equal to matrix, or you can pass the name here as well, right? And you can see that how many parameters are we are calculating. So you can calculate the parameters. We have 61 features. 10 is the neurons that we're adding. So 61 multiplied by, uh, sorry, 62 because we are adding the intercept as well in the model. So 62 plus 10 multiplied by 10, sorry, 620. And then next 10 as well in the next hidden layer, 110, then 11. So we get 741 is the total parameters that we have. So including the intercept, we are adding one more. That's why. Okay, so how do we call the, so this is the model summary that we get. And then how do we call the model? Bin class model I am calling, and then binary classification, the function that I'm calling, and passing the input and metrics here. And you can see how I'm running. So I'm fitting my model on my train data, validation data, batch size, epoch, right? So we have, you remember we had fixed 50 epochs. So you can see that we have 50 like times the model will run, and you can see how much accuracy we are getting. So at the end, we have 99.83 on the training data, and validation data, we have poor accuracy, 82%, right? So this is something we can say an overfitting problem, but again, overfitting, we have to make sure that whatever pre-processing part we follow in the train data, we also follow the test data, because if the difference is, yeah, 5-10%, then it's okay, it's overfitting problem. But if the difference is more than 15-20%, then it's a different problem altogether. You have a different distribution of the data. So that's where we need to take care of in the data pre-processing part. But yes, like by broadly I can say, yeah, model is overfitting. We need to take care of that. How do we do that? That's the hyperparameter optimization process of the neural network, which I have captured, I've covered here, but we don't have time to cover that in detail, the 6th point here. But you can definitely have a look. What are the parameters we have? I told you the optimizer, like the stochastic gradient descent, mini batch, Adam, all these are hyperparameters. Learning rate is one of the hyperparameter. Batch size, epoch, all these are hyperparameters of a neural network. You can use grid search CV as well to tune them all together. But again, if you apply that, it'll take a lot of time. Okay, but how do we save the model? Yes, we have saved the model here. Once you do that, you will see that like it'll be folder, it'll be created. Once you follow this path, a folder will be created here. You will see the I mean, your model will be saved. How do you load the model? I have given the command here in this previous one. I think forgot to cover that. You can load the model back. It's the same way we load the machine learning model. Same thing. Predictions, recall, precision recall 99% on the train data, test data is 70%. So we are not that good in predicting the ones which we need actually. So that's why we definitely need an optimization technique to overcome this problem. Okay. How are we in terms of doing validation loss and accuracy loss? You can see the accuracy. You can see that this is what it's happening. Okay. See, dead neuron problem is the same thing. Like the activation function, if we talk about, right? So the on the edges, I told you, right? The slope gets, steeper. So sorry, flat, right? So there we have a dead neuron problem that we can't, which means that what happens is that once the gradient or the slope gets lesser and lesser, smaller and smaller, the value of the neuron gets slower and slower. Sorry, lesser and lesser. Right? It close to zero, which means that it's a kind of dead neuron problem. It's a kind of dead neuron, right? So sigmoid, tanh, all these functions where we see the flatness in the on the edges actually face a dead neuron issue. So that we need to, so there are techniques like momentum, you can say, or you can say RMS prop, or the other these techniques we try to overcome the dead neuron problems. Basically, there are better algorithms available in gradient descent, advanced algorithm, which tackles this problem. Or other, activation function as well, like parametric ReLU, ELU, all these ReLU function, activation function we apply to handle the dead neuron problem.
Is scaling necessary in linear and logistic regression?
No, I told you, right? So it's even it's not necessary in the neural network as well. But again, if we do it, like in linear and logistic, if I talk about, no, it's not necessary. We don't do that. But if you're running a ridge regression, lasso regression, then it becomes important because you have learning rate and other parameters like the the I mean there you optimize the parameter which minimizes your I mean the MAE and L1 regulation and L2 regularization problem. Sorry for that, I forgot that so part. But being L1 L2 regulation, they require a normalized data. I mean, although again there as well you don't have to, but it's better if you use that. The scaling part we do mainly in whichever algorithm it is, apart from few distance based algorithm. If we try to use any other algorithm, they are to improve the speed and what you call the smoothing of the process. That's the only thing. The scaling helps. Otherwise, scaling doesn't improve your accuracy. Scaling doesn't improve your anything related to your model accuracy metrics, I would say. It only helps you in processing the data, optimizing, converging your algorithms. It might be little faster or optimized algorithm you will get. Apart from that, scaling doesn't help anywhere, but it doesn't harm definitely. So people, that's why people use it. Then question comes is, okay, why people use it all the time? It doesn't harm. It makes your process a little fast. It doesn't harm the algorithm. So why don't we apply that to get faster results?
This session is about applying deep learning models into stock prediction. Uh, I would like to largely focus on the concept, how deep learning model is being applied in time series. We would have so far gone through how to apply deep learning models in cross-sectional data. Right? We would have not seen in terms of time series data. So this is what the session is all about. I'm assuming a lot of you would have already completed the time series module, but if not, for those who haven't completed it, I'll anyway start from the basics. So what is time series forecasting? It is actually an attempt to forecast the future values by understanding the past values, identifying repeatable patterns, and forecast the future. If we compare the same to the cross-sectional data, this is no different, right? Even in the cross-sectional data, we do a lot of bivariate analysis, and we build the models based on the patterns we identify from each independent variables towards the target variables, right? Similarly, we also going to identify some patterns in the same time series. Only that here there are no X and Y, only there is only one variable, which is time series. And the only independent variable attached to it is time, which is basically the date. Right? That is the only, to put it in a simple terms, you will have only one column in your Excel sheet. Right? That is what the time series is all about. So when I said patterns, so cross-sectional data is nothing but the data that you guys have been working on, right? You have, let's say you have 10,000 rows of your customer data, which was collected at different time series, right? Some data would have been collected yesterday and some data some 6 months before, 1 year before and all that. So they are not time dependent. So we collectively work on those 10,000 customers and we do some analysis. So we don't assume any time recency or older data and all that in cross-sectional data. When it comes to time series, it is dependent on the time, right? It has to be sequential. So when I say sequential, if you look at the plots, I have given 4 plots here, which starts from 1970, early 1970s to 1995. And the same goes for the Australian quarterly electricity production. It starts from about 1955 to 2010. Right? So this has to be in an orderly basis. Remember the random stage shuffling and all that, the liberty that we have in cross-sectional data, we cannot do that here. So we will have to depend on the order and we should not be changing that, right? And when I said patterns, in cross-sectional data, we identify a lot of patterns, like if age is increasing, the insurance premium amount increases, right? These are some of the patterns we identify. And based on that only, our model gives us some prediction. Now, what are the patterns that you have in time series? Right? You don't have any X variable. You have only one column, which has any, let's say if it is a sales data, you have only sales. Let's say monthly sales data of Flipkart for past 12 years, right? So 12 into 12 months. So you will have about 144 data points with you. With that one column, what are the patterns that you can identify? If you plot it against the time, businesses leave some patterns, right? Any behavior leaves with patterns, not just with human, it's all in the business as well, right? So if you look at the first plot, this has a very good seasonality on yearly basis. And also overall, it has a very strong cyclicality, right? There is no trend in the data largely. Together, there is no trend, but we can see a seasonality that is there in the data. When we move on to the next one, this does not clearly have much of the seasonality, but we can see a strong downtrend. So the pattern that is prevailing in this series is largely dictated by trend. And here it is all about seasonality and the cyclicality. Looking at this plot, we have the strong trend for the past about 50 years, and we have a very strong seasonality as well. So together, trend and seasonality can dictate about 80% of the data. But if you look at the last one, this is where when you pitch in some real-time scenarios, you get data like this, right? Where you don't find any pattern, any trend, or any repeatable patterns, right? What can you do when you have this kind of data set, when there is no pattern at all? This is where models like deep learning models helps you a lot. It helps you to pick up the noise as well in the data. We will first see basic steps in forecasting. This applies for traditional models, deep learning models, most powerful deep learning models. The steps are one and the same. And this is as well in the classification and regression models we've seen, this is almost one and the same. The problem statement, let's say in terms of time series, what kind of problem statement that can come? I want to forecast the future of, let's say, sales, or let's say the profit of a company. I want to forecast for next 1 year or 2 years. Based on that, the company can plan the budgeting, right? In terms of production, how many, let's say Hyundai wants to forecast how many cars demand will be there for next 1 or 2 years. So based on that, they can plan their production and all that, right? So this is one thing I wanted to say at first beginning of the session itself. This time series has advantage of application throughout any industry or any business that you can pick. And the second advantage attached to it, the data availability will be very easy compared to the other cross-sectional data. It will be readily available in the MIS, and you can just pull it out and you can right away work on building the models. Right? That is why if you see a lot of projects, a lot of startups, a lot of analytics company, they initially focus on building time series forecasting. Right? So that's problem statement. Then we can gather the data, which is quite easy in terms of time series forecasting. This applies for the stock market as well. You can just log into nsindia.com if you're in India, or nizy.com in USA, and you can just right away download the data. It is free of cost. There is no time that is involved at all. It is in terms of seconds you can download the data, right? So that is the advantage of time series forecasting. And understanding the data, here is where we generally use EDA, but understanding the data is where we do EDA in cross-sectional as well. Here we will do a different set of descriptive statistics. I'll show one of the descriptive statistics that one plot can explain the entire EDA of time series forecasting. So we will understand what kind of patterns that are there available in the data, and based on that, we will start choosing and fitting the models, right? And then once fit the model, then we can just evaluate. And what are we forecasting in time series models is just the real numbers, right? Like a regression problem. So what do we do in regression problem to evaluate? We get RMSE, MSE, MAPE and all that, right? So we will apply the same methods here. And more importantly, there also we use RMSE more frequently. Here also we will use the same. And once we are happy with the model, we will forecast the future. Right? Let's say I have 5 years of monthly data. I will have 60 data points. I want to predict for next 6 months. So I can do that. With the model that I've built, the model would have learned the past patterns, and it will tell what are the kind of patterns that you can expect in the next 6 months. Right? Looks charming, but there are some problems. See, these are some of the forecasting models, traditional forecasting models that were there in the history. These are the kind of models that are there for more than about 60, 70 years in the history, right? Like average method, just getting the mean value and saying that on an average, let's say Virat Kohli's average is 50. And if someone asks what is the score that he'll score in the next match, people will say 60, right? 50, I'm sorry, because his overall average is 50. that isn't a simple forecast. The naive forecast is what he had scored in the previous match. We assume he's going to score the same in the next match, right? Seasonal naive is almost like the naive, wherein which if it is a seasonal product, let's say Apple sales, every December we see higher Apple sales. If that is the case, then this month is a December month. We will say what was the last December month sales, right? So, and drift method is giving some amount of change over time so that the business keeps improving every year and month and day, right? So we cannot say yesterday is going to be today. So we will give some amount of increase so that it will keep on going upside, like interest rates or let's say GDP of any country, it keeps increasing with a small amount of change, right? So with just drift method, we can predict that. And exponential smoothing method with just, if your time series has only trend, you can use double exponential smoothing. And if your time series has trend and seasonality, you can use triple exponential smoothing. Right? These are very, very basic models. Don't just focus on the names. These are completely simple models. I'm not getting into all this because these are traditional models. Most of you must have already known if you have done the time series forecasting modules. If not, these are very simple. This is the only EDA image that I wanted to show in terms of time series forecasting. This is a data of air passengers data. And this is the original data. The top of the chart is basically the original data. And we can see there is a strong trend plus very strong seasonality as well. And we can see the seasonality over the time is keep increasing. Right? This is how the real business also, right? Every year, the air passengers keep increasing. And during the festival time, we see strong demand for the aviation. Not even for the festivals, even on the Saturdays, Sundays, right? Weekends, peak hours, non-peak hours, we see the stable seasonality always, right? So that's why we are seeing a very clear pattern in this. But just by looking at the plot, we cannot assume the patterns are going to dictate the entire time series. This decomposition function helps you to split out all the patterns that are available in the data. If you look at the second plot, this only gives the trend that is prevailing in the entire series. This trend is nothing but the 6 months average. Let's say at this level, what is the past 6 months and next 6 months average, which is basically called as central moving average. So based on the past 6 months and the next 6 months, it will calculate the average value and it will keep moving the window. At any point in time, it's previous 6 months and the next 6 months. That average value will be calculated here. So this gives you the clear trend that is available in the data. The next one is seasonality. It calculates the percentage of change at this point compared to the previous point, right? Compared to the previous seasonality. So and the total changes average is the one seasonality change. And if you look at the last one, this is nothing but the residuals, or you can say error, or you can say remainder of the time series, which means whatever that is left after trend has been sucked out and seasonal has been sucked out, all other random values will be displayed here. And we can clearly see the traditional models can only pick these trend and seasonality, right? If they were to pick only these two, they will certainly not include this noise in their model prediction. And we can see some more information is also left in the model prediction, right? In this random values. We can see some patterns also there left out by this decomposition. So if I build a model around these values, probably I'll be leaving these things, right? This is where the need for deep learning models comes in. Right? Another model, which is the last model in traditional model, is quite powerful model, which is auto-regressive moving average. We normally call it as ARIMA model, which is nothing but the linear regression, right? We already know what is linear regression. Given the X, what is the Y, amount of change in Y, right? Which is nothing. Auto-regressive means the regression over its own series with its n number of lag values. Let's say in this series, if this is the value, this value is being dictated by the 12 months before the data, right? So if I give a lag value of 12, the regression will take cues from this value and it will predict this value. And it also keeps an average of errors as well. So it calculates an average of errors and it will also add here. So this is an attempt to bring in this residuals into the model. So the model will also learn some more bit of the residuals that is left in the time series. Right? That is why ARIMA is still a traditional model, but quite powerful than the other average exponential smoothing models and all that. Right? We will not get nitty-gritties of all this. Eventually, you will learn quite easily all this. Our agenda today is to apply the deep learning models, how to handle this part, right? How to handle or how to take cues from this residuals. We will be looking at Bharti Airtel, which is listed in Indian stock market, and a company which is known for everyone. Right? This company is trading at 525.45 as on yesterday's close. And I have taken data till 29th June, which is 3 days before the present. So using that data, which is this data, using this time series plot, let us predict next 5 days or 10 days what is going to be the trend for Bharti Airtel. Right? As we can clearly see, this is stock market. There is no repeat in trend, right? There is no repeat in pattern. Every day morning is new to stock market, right? So one thing that is guaranteed in stock market is nothing but the randomness. Right? Anything can happen. That is the only thing you can guarantee in stock market. Nothing else is guaranteed. Right? I've been in the stock market for past 10 years, so I can quite understand that. And this statement holds true. So given that anything can happen today morning, so how can I build the model around it? You can still develop some sense around it. Let's say if Bharti Airtel has moved up by 5 for past 5 days, if the stock is going up, what will be happening on the 6th day? Right? Here you need a human brain to think about it. What if I replace that human brain with a neural network model? That is an attempt of bringing in deep learning models, which is particularly ANN into time series forecasting model. Right? So we can clearly see there is no trend and obviously no cyclicality, no seasonality, no patterns that we can see here. Right? So let's see how we can build the deep learning model around it and still predict. So we will start with the neural network. See, ANN is nowhere related to what we are going to learn today. Right? We are going to learn RNN and LSTM, but the base of it comes from the artificial neural network. First of all, we all know it is a powerful model. Why is it powerful model? Because it learns from each data point. Right? If you the next powerful model that we've learned in our academics is random forest, right? And we all know it does not go row by row, right? It compares the column by column towards the target variable, which variable has the largest proportion. Based on that, we split the data, right? We don't learn with each rows and each observation, right? In terms of ANN, we pass on each rows and we understand. We initially assign a weight and we calculate the error and we do back propagation to bring down the error, right? So that is why, first of all, ANN is powerful because we learn from each observation. That is one thing. And the second thing, the hidden layer is what makes the learning very deep. Right? As we can see, neural network is simply X values, which is your independent variables, assigned with some random weights initially. And we will apply some activation function and we will calculate the final value. Right? And what are neurons here? Neurons is nothing but the parts of hidden layers, wherein which it starts within 0 to 1. And if it crosses a certain value, that particular neuron will be lit up. If it does not cross that certain value, that neuron will be avoided for that particular observation. Right? Let's say I want to eat samosa, and let's say today it is raining, and I also have a fear of obesity. If I eat samosa, I have a fear of obesity, and let's say the shop is not hygienic, whether the shop is hygienic or not. Let's say I have 3 variables now, whether it is raining or not, Do I have the fear of obesity or not? And if the shop is hygiene or not. So I consider these three factors to decide whether I need to have a samosa or not. Right? Let's say out of all this, I think hygiene is the important factor I consider before entering into a shop to decide whether I have to have the samosa or not. Right. So what I will do, I will give higher weightage to this. Let's say I give 6 and I give about 1 and 1. So these now I will have some values here. If I in my data set, I can just multiply them with the weights, and I can add all these values. I'll get a final value. Right? Let's say I get about 10 here. I pass on this to an activation function. If my decision is whether I'm going to take samosa or not, it is going to be a binary classification wherein which I'll apply a sigmoid function, because I have to constrain this value within 0 to 1. Right? So I will apply a sigmoid function, activation function as sigmoid function, and based on that, I will decide what value I'm going to get. Is it 0 or 1? Let's say I get 1 here, then my prediction is 1. But this is just half of what deep learning is all about, right? Particularly ANN. This is forward feed. And once this learning is done, we once again compare with the actual data. We have the advantage of trained data with us. So we can compare the same with the trained data. And we do something called back propagation. Right? With back propagation, we have actual Y value and my predicted Y value. So this will give me the difference, which is basically my error. And my objective in terms of back propagation is to bring down this error. Right? This is where we follow a gradient descent method. Let me just, let's say I get error of -5, -4, -3. These are my errors. And probably I'll have to be squaring it, right? We generally square the errors. These are nothing but the squared errors. And how do we achieve the parabolic structure? Just plot this. So here's where we achieve this looks like a big smiley, but this is a parabolic structure. And this is how we achieve this parabolic structure when we plot all the errors. Now, if this value is this side, it means these are negative errors, right? Let's say my error is at this range and my slope is going to be at the downside. When my slope is at the downside, I'll have to increase my weight, right? My actual error is below the actual value. So I'll have to increase my weight so that it'll go somewhere close to 0, right? Close to 0 or above 0. We tend to achieve 0, right? So I'll have to increase the weight. So in this case, I will increase the weight. And if my error is on the right side, which means my error is 5 points away from 0. So I'll have to bring down the weights. Now, this is what gradient descent does, right? It either increases the weight or brings down the weight, and it ensures the error is brought down. While this is being done, there are a lot of methods to do this, but gradient descent is an attractive algorithm where it keeps the learning rate at a lesser pace, right? It is once again a randomness of assigning the weight, right? In terms of randomization, when we give a very lesser learning rate, it keeps reducing the weights. Let's say in terms of here, it keeps reducing the weights in a slower rate. And when it nears to the suboptimum error level, it slows down the learning rate to a further level. In case of this, it increases the weights, and the rate of increase in terms of weights will be slower when it approaches the suboptimum level, which is actually 0 error, right? This 0 error. This is what, on a nutshell, a gradient descent does, right? So I'll just drop all this. We spend time on ANN. Now, this is powerful model. We can all agree on that. And you would have seen some splendid accuracy in your data sets as well. And even if you apply them on the real time, people get very good accuracy. But what is the problem with neural network is when you work with the sequential data, right? Even though this learn backwards, if I give one customer, let's say one day I predicted my samosa and it gives me, okay, that day it was not raining and I had a fear of obesity. So I did not eat samosa one day. But next day, the things will differ, right? Not just if I don't eat samosa yesterday, that is not going to affect my today's decision, right? I will once again see whether it is raining or not, the shop is clean or not. Still, I have fear of obesity and all that, right? So yesterday is completely independent of today. The trials are completely independent. And if you have a data set of 10,000 customers, one customer defaulting does not affect the other, right? So when there is that kind of independency, neural network, artificial neural network will work well. But what if I have a sequential data? When I say sequential data, this is what I mean. It is associated with the time series. I cannot break in or I cannot shuffle it. Right? It has to be on an orderly basis. Some of the sequence data, time series data, let's say sales data, which I've shown here, sentences in terms of writing sentences. Let's say we want to know what Donald Trump is going to tweet next, or Elon Musk is going to say. Let's say he started typing tweet and we want to know what he's actually going to type about. Right? This has to be in a sequence basis, right? Sentences. And same goes for audio and a voice transformed between there are a lot of NLP techniques applied in decrypting the audio between the armies and the military and all that, right? So these are all basically sequence data. And once again, the music as well. These are all sequence data. We want to know what the next beat is going to be. Is it going to be a high beat or low beat, or the bass is going to be high or low? If you want to predict that, then the order cannot be changed for that data. So when the sequence is there, the independence is there, right? If the stock has gone up yesterday and today the chances of it going up will be there, but it will not be higher, right? That is the nature of stock market. Stocks cannot keep going every day, right? So that is sequence data. This is one more example I can give is, let's say CSK is playing and last 5 matches, we look at their track record, right? Win, lose, and win. Based on that, we will predict what is going to be the next match, right? With just one match, if we predict, it will not be better, right? We look for the form of that particular team. This is basically the sequence data. And if you look at the example that I've shown here, I'm not sure if it will be quite, visible or not if you are watching it in mobile. But if you are typing something in your Gmail, let's say here with attaching my resume, kindly, and it will automatically say do the needful, right? It will automatically predict that for you. And this is possible because it is a sequential data, and this is because of an RNN, the algorithm which we are going to learn today. Right? This is once again a neural network model, but works on a sequential basis. Right? There are 2 kinds of method that are there in RNN, which is many to many, many to one. Let's say if with past 5 days of my data, I want to predict next 2 days or 3 days. Or let's say if you look at this example here with attaching my resume, I'm not predicting the next word. I'm predicting next sequence of words. Right? This is called as many to many inputs and many outputs. And sometimes it can be many to one as well. Let's say I give last 30 days of stock price data and I want to just predict what will happen tomorrow. I don't want to know what will happen next 5 days. I want to know what will happen tomorrow, how the prices will close tomorrow, just one day. Right? The same applies for the CSK example that I gave. Last 5 minutes data is with you. What will happen on the next match? This is basically many to one. Right? RNN really works well with many to one cases. And in terms of many to many, it still works well. As you would have seen in your Gmail, the error will be very, very lesser in terms of prediction. It will really work well. But to start with, when you are starting to learn deep learning models, I would recommend to start with many to one. Particularly in stock market, you cannot keep saying what will happen tomorrow, day after tomorrow, and the day next to that. Right? No one will believe you. And the same applies for the neural network also. It is very hard to keep forecasting. What happens here is the problem with keep on forecasting is, let's say, this is my data and I forecast the next day. This is my next day. And if I forecast the next day, this is something here. What happens here is if I have to forecast this point, my model has to rely on this point also. And what is this point? This is not an actual point. This is my forecasted value. This will have some noise. And if I keep increasing my forecast, what will happen? I will keep accumulating my noise. Right? So you predict noise over noise over noise. So that's why keeping more amount of forecasting is not an ideal practice. Keep it to a restricted level. Right? So this is about sequence data. And how does RNN helps here? RNN is basically a recurrent neural networks. And this basically works in a sequential basis. What we are seeing here is a structure of an ANN, wherein which you give an input value, get the summation of it, the weights and the input value, just add all of them and apply an activation function. Then you will get an output, right? Let's say I apply a ReLU function here. What we are seeing here is a ReLU function for a regression problem. So if the value is 0, it will not give any output. If it is greater than 0, it will give an output. Right? Let's say I've given age, gender, and my salary. What is my insurance premium amount? So I can predict it using the ANN. When it comes to recurrent neural network, let's say yesterday's value or the yesterday's moment will impact today. Let's say stock market, I'll have to use RNN, where the structure is quite different, but it is once again simple. If you take at this level, the input at T is today. This depends on what happened in T minus 1. The amount of change that happened in T minus 1 will be passed on to the today's prediction also. It will be added with the current summation and together it will be given with an output. And this output, this degree of change will once again be moved on to the next day and it will be added to the previous calculation and we will get the output of T plus 1. It is completely on the sequential basis. Let's say if I have 500 days of data, I will have 500 days of this structure. Right? And we can see we are applying a neural network model. This is almost like ANN on each single data point. Right? That's what makes RNN a powerful one. Right? And so this way, the sequence data has been handled once again by using the ANN. The little tweak is we get the cues from the previous day as well. Rather than relying on every single day's prediction, we also get the cues from yesterday's change. Now you can understand one thing. Now recurrent neural network needs a data set that has connection between the days. It need not be yesterday only. It could be last week or 1 month before or 1 year before. But the connection has to be there. The dependency has to be there. If that is not the case, then once again applying RNN will not be useful. Right? So this is one of the assumptions that you need to keep in mind before building a model like RNN. And what kind of questions that it answers? Let's say, does consecutive 3 upsides, let's say a stock goes up by 3 consecutive days, will it create a strong upside trend or not? Right? Or the same goes the opposite way. If the stock keeps coming down, is it going to be a downtrend or not? And we are going to also answer whether the bar theater is in downtrend or uptrend. Right? And of course, a disclaimer here, this is not an advisory or recommendation class. Don't take it that if you apply RNN model, you can keep taking profits out of stock market. This once again involves what kind of data that you're going to give in. When I say what data, what kind of company. I've chosen Bharti Airtel here because of a particular reason, which I will anyways explain during the session. Right? Without that details about the company, if you apply RNN, you have a lot of chance of going into losses. Okay, so don't take it as a recommendation or advice. This is just to teach how to apply this technique on the real-time data. As I already said, the structure of RNN works like this. If I keep it in vector format, if I just bring it in this format, RNN is today's data. This is my today's X values. And I also get the previous value, previous day's vector. And I assign the weights, I calculate the new one. And I keep predicting it. And the today's prediction will move on to become, tomorrow it will become yesterday. And tomorrow's data will be given here. And once again, the prediction will happen. This is basically a cyclical action. Based on this, if you have 500 days, this will run for about 500 times and it will give the 500 days of prediction. Right? So one of the powerful models, you can understand now why it is powerful. And the math behind it is how does it operates? Of course, there has to be equation, right? So let's say previous day, x0, there will be a value. We will assign some weights and we will find the h0. And from that, we will apply some activation function with weightages. We will find an output value. This is for one particular day. And from there, I will take this change of level of change to the next day. I will just add this value to the next day. And I will also get the next day's input. Together, I will apply the activation function and I'll predict the next day. The equation goes like this. HT, which is this middle layer, which is hidden layer basically, is equal to, this is just an activation function. I'll come back to this. The weightage into xt, this wi into x1 plus the previous day weights, this weight plus a bias. I have not talked about bias so far yet. So we will discuss about bias here. Bias is nothing but a threshold that we set. If that particular neuron does not cross this level, don't activate that neuron, right? So bias is like, as I said, setting a threshold. You make your model little bit tougher, right? Let's say in a pixel, if there are 3 levels of pixel, let's say mid-level and very darker level of pixel and a very lighter one. Right, so let's say this is medium, this is very intense dark, and there is no color at all. Now, if all these are basically neurons, and if I want to activate a particular neuron, I will say if that content within that pixel has to cross a certain level, let's say if I fix a bias of 0.1, there has to be 0.1 gray color in that pixel. Then only I will activate it. Let's say think about an image like this. This is a picture and it has a number 1. If I just zoom this, you will know this image will be break into pixels. And these pixels will be darker and all the other pixels will be lighter, right? All the other pixels will have 0 value and the central part will have 1 here. This will be 1, all the pixels. And there will be some pixels that will be connecting the whiter part and the darker part, which will be on a medium level of gray level, which will be 0.5 of gray color. Right? So neural network just assembles all this data and it will identify this pattern. Right? Similarly, the same applies in the RNN as well. The bias is one and the same for ANN and RNN, where here we set if that image gray color is not above 0.10, consider it as a 0. Some images will be having, let's say, 0.05, right? But neural network should just ignore that. So that is why we give a bias value, so that even a lighter gray level will be ignored. They are not an actual data, just noise in the data, right? So same way we apply some bias here as well. See, stock market will always have some volatility, right? Let's say 0.1% of volatility every day. If I add bias, I will say that you don't consider that 0.1. That is normal in the business. I don't want to make prediction out of it. That is why we fix bias. And we can, now when I say fix bias, we consider bias. We cannot fix bias here. The model will take care of bias and it will calculate automatically. The Adam optimizer will automatically calculate the best bias rate. Right? This way we can calculate the hidden layer. Once we calculate the hidden layer, the y value is nothing but the activation function into the weights that you get here plus the bias. right? So this is the math behind the RNN. This is applied on every data point. We see 3 data points here, which means we are predicting 3 days of data here. And if I have, as I said, 500 days, it will be having 500 network like this, all connected within each other. That's why they are network. We know that. Now, what happens in terms of back propagation here? Now, we said it will keep remembering the past values, right? Yesterday's values will be remembered today. But what if I have a data which takes cues from the past month values, not the current day value, the past month value? The problem will be the more importance will be given to the previous day, but not for some values, which is there, let's say 1 month before. That is the problem in terms of back propagation. The weightages will keep decreasing when we increase our back propagation. When we start, let's say I have a value today and yesterday, day before yesterday, and I go on to the past. The weightages will keep declining. How it will decline? Let's say, look at this formula. This is how the weightages are calculated in back propagation. Weight W is equal to weight plus delta of change in weight. This delta change of weight is nothing but the learning rate, change in error, the percentage of change in error divided by percentage of change in weight. Right? If this value is lesser, since I go deep into the past, this value will be keep decreasing, right? Because for every iteration, I will bring down my error. When I bring down my error, I will also bring down my weightages. So there is less possibility that I will take Q from this point to the future point. But more weightage from this point will be given to the future point. Right? If dE by dW, which is the change in error by change in weight, is far less than 1, let's say it is closer to 0, then this value will not have any value at all. Then you will have that particular day point's weightage only. Right? So which means this is not taking Q from the deep past, which is basically called as vanishing gradient. Right? We moved on from ANN to RNN because there is no memory involved. And when we came on to the RNN, we now realize that memory is there in the RNN, but it is not that deep. It is able to remember yesterday, but not, let's say, 1 month before. Right? Another problem. So problem after problem. All these days, we would have been under an impression that ANN is one of the powerful model or complex model to understand. But I think by now, you will feel that ANN is better. So great. So this is model training in terms of RNN. Now, how do we take care of this vanishing gradient? Right? My weightage should not keep going down like this. This is where the next technique comes in, which is long short-term memory. And here, what do we do? This is once again layer by layer, like what we saw here. This is first layer, and this is second day. This is third day. This is first day, second day, and third day. I will not dive too deeply into LSTM. This involves some lot of calculations, but they are not complex calculations. They are very simple calculations, but it involves about 4 or 5 lines of equations. Right? I'll just give an top view on this. This is one neuron. Within that one neuron, what are the things that are happening? Long short-term memory, the need for this is because a neural network has to take cue from long-term dependencies. Let's say I have a 500 days data. I also want to give equal weightage to the first day of the data, or 100th day or 200th day, any past value. I want to give equal importance to that. Why is this required, particularly in stock market, is because let's say what happens to a stock if it goes up by 5 days continuously. People will start selling it. All of a sudden, next day, the stock price will come down. But once again, it will not once again go up by 5 days, right? It will go into some other different pattern. And after 1 month or 2 months, once again, this might come back to the same pattern. Like every day, it will go up for next 5 days. Now you want to know what will happen on the 6th day. Now that is where neural network can come in and say, I think this is the kind of pattern I've seen already. My model, I've learned that. And based on that learning, this should come down tomorrow. And that is how I want to build time series forecasting model, not on the average, or because average smooths out everything, right? So I cannot always rely on the average. Will you say Virat Kohli will score the average score next month? You will never say that, right? You will apply, let's say if he's playing in England, you will know when was the last time he played in England and what was his score, what was form then, right? You will ignore all the matches played in between. What was his form in Australia, New Zealand, India once again. You will only focus on the current England series with the past England series, right? This is where you need the help of long short-term memory. Right? In terms of RNN, you will forget that. Your model will, when I say your model will forget that. But here we can give some importance. And how do we do that? Is by using a function called tanh. In your ANN, you would have learned an activation function called tanh. Sigmoid is basically 1 and 0. Relu is basically for a continuous variable. Tan h is basically at a 3 level, which is 1, 0, minus 1. The advantage is if there is a negative trend or negative impact, the degree of change is on the negative side, it will clearly tell you. In terms of sigmoid, it will still fix it within 0 to 1. So you will not know which is negative trend and which is positive trend. In terms of tan h, you can bring that. And how does it work? How does it remembers past values? Let me give you the. So this is going to be the final slide. If you are worrying, are we looking at too many plots today? So this is the function that is happening between one layer to the other. When I say layer, it is between one day to the other. What happens here is the input layer, this input comes from the past degree of change, right? This is past H value, previous day H value, and this is today's input, right? H0 plus X1. That value is my input to the next layer. And here I apply something called forget gate. If previous day's momentum is not related to current day, the sigmoid function will say whether it is related to previous day or not. Let's say 0 or 1. If it is 0, it will be forget here. Right? The model will drop that memory at all. If it says no, it has some value and it has a relationship to today's change, then the next sigmoid function will add it to a function. Right? So whatever values that is not related, it will be forget first of all. And whatever is required will be moved on to the next level. And here is where we apply something called tanh function, the blue one. Here we fix the weightage between -1 to +1. Let's say if it is -1, it means an inverse relationship where yesterday, if it has gone up, today it will come down. And if it is +1, it means yesterday gone up, today once again it will go up. Okay? That is what tanh gives you. If I don't apply tanh and if I apply the value right away here, let's say the value is 10, and if I multiply that, it will keep increasing by every day, right? And your forecast will look like something like this. And your actual values will be somewhere here, and your forecast will look like this because you haven't brought them between 0 to 1 or -1 to 1, right? So this is vanishing. Yeah, I'll come back to the exploding gradient, but this is vanishing gradient that I'm explaining about. So once that is added, the value that is required for the model will get multiplied and it will be added to something called cell state. This line that passes through each layer is called as cell state. This is basically the memory of the model. This line will pass through all the days, all the layers inside the model. Right? And once this has been added to the model, it will start giving the output. Okay, so these are the components of it. Of course, when we look at the mathematical part, it will add a lot of sense, but it will be too much. Now, once we see how it has been applied here, and what is the input of the cell state? It is nothing we are calculating here. The input of the cell state is the past calculation. I think someone is using annotate. Can you just remove it? Okay. Okay. So this cell state, the input comes from the previous values and the new value will be calculated here in terms of multiplication. This is point-wise multiplication, and it will be added to the previous memory. If it is an uptrend, then cell state will have an uptrend. Right? So this LSTM has about 5 parts, which is forget gate, input gate, output gate, cell state, and point-wise multiplication. Right? Which is 0.5 function, either it is a multiplication or addition. Now, I did not explain about one more gradient called exploding gradient and how to handle it. Let's say I know my, so this is, sometimes this is not possible, but I'll give you an example. Let's say in my stock, I know very well about my stock, and I can very clearly say only the past 10 days affect my current day. The traders or investors of my stock do not consider more than past 10 days. If that is the case, it is completely not possible in stock market, but it's certainly possible in some other business. Let's say in auction market, only 10 days window, people can buy within only 10 days. So if someone wants to sell, he would have bought only next past 10 days. So you want to know what price he will quote. You can say what was the market momentum in last 10 days. And I don't want to calculate anything beyond that 10 days. That is where you can use something called exploding gradient, wherein which you can pass in a clip. When I say clip, it will remember only the memory in past 10 days. If I say clip is equal to 10, it will remember only the past 10 days and nothing much, right? So that is exploding gradient, but the use case for it is not that good these days. And vanishing gradient is very popular because the computational power and the supporting mechanism is very good these days. Until that, people were using exploding, but these days the vanishing is being used very easily and quite comfortably. And I will explain why vanishing is being used these days, and particularly why deep learning models are into the talk these days. Even though these deep learning models were there for past 5-6 decades, why are they spoken now? Because if you go into your Colab, there is something called GPU, right? GPU board. This accelerator helps you to do powerful computation, which was not possible decades back, right? And only this, because of this, there are a lot of neural network algorithms that are possible these days, right? And my advice, if you are running, always run deep learning in Google Colab. If you are having a lesser RAM size, like say 8 GB or below that, it is always better to go with Google Colab because this offers you about RAM space of 13 GB. And it comes with an advantage of GPU, right? It will be by default none. You'll have to go to the Colab and you'll have to change it to GPU, right? So we will see how to, we've seen the concepts. Let's see how we can apply the same in the data set. So I'm just bringing in the usual pandas, NumPy brothers, and Matplot. I'm reading the data set, read Excel, Bharti Excel. And this is my data set that I have. I just removed all this. This data set I downloaded from nseindia.com from historical prices. And of course, it is free of cost. And it comes with a lot of prices: open, high, low, previous close, last traded price, and what is today's close, right? And my subject of interest is on today's close. And this comes with VWAP. If someone is already in stock market, you will know this VWAP, volume, value, number of trades, and all that. In terms of time series forecasting, you don't have just to predict the prices. You can also predict the number of trades also. Whether a lot of people will be interested in my stock today or not, right? It's not just the prices. With these mechanisms, you can predict the value, what will be the volume tomorrow, what will be the number of trades, will there be crowd, or the number of traders will be increasing tomorrow or not. Everything you can learn and start forecasting, right? Today's interest is on predicting a stock price. So let's just focus on this. So my new data set will be just one column. You can do some multivariate analysis also. This feature engineering is something that I strongly recommend you to follow. Most of you must be already doing it. I'm quite sure about it. But if you don't know about it, please start exploring about this, because this is what will separate good data scientists from an average data scientist. Right? The data is one and the same for everyone. The algorithm is one and the same for everyone. Right? You can do some hyperparameter tuning and all that, but still not much of a difference that you can make. The difference that you can make is how well you read this data and how well you bring in some new information. Right? Let's say 5 days trend. I can create a new variable, 5 days trend. What is the last 5 days trend? Is it up or is it down or is it flat? Right? Was yesterday a high volume day? Right? If it is a high volume day yesterday, nobody will look at that stock today. They will move on to the next stock. Right? So if you want to trade, you want to know whether people will come into the market today or not. So I can say high volume, right? 1 or 0. And this perhaps can be 1, 0, or let's say this is 2, 1 and 0. I can create a label encoding also. And I can keep on increasing a lot of feature engineering. At once I went crazy and I built about 100 plus variables. And that is what the difference that makes, right? What are you teaching here? You are teaching the pattern to the data set, to the model. I'm sorry, right? You are getting the pattern and you're giving it to the model. This is just the data. If models are performing well on the data, think about model performing on the patterns. It will really relate to the real business world and it will give higher accuracy, right? And you can strongly rely on the output that you get from the model. Right. So that is basically multivariate time series. We will not be covering that. I hope that is not the same in your academics as well. But the algorithm is one and the same. The codes is one and the same. You just create feature engineering and get new variables and apply the algorithm. Okay. One thing I wanted to say. So I'm bringing in the data set along with pandas pd.read Excel. Of course, this is an Excel file, not CSV file. There is a super cool function called past dates. This helps you to help Python to identify the date by itself. Yeah, and I will be sharing this Colab file to all of you. So don't bother about typing now. Focus your time on listening to this. And past dates is equal to true will help the pandas to realize that this is a date variable and not a numerical variable. And if I mention index column is equal to date, it will automatically become a index column, right? And I get the info of it. We can say all the variables are in either float or integer. The variable that I'm interested is on the closing price of Bharti Airtel, right? So I'm just getting that df close dot plot. This space is there because in the data set that you download from the NSC itself, there will be a space. There will be an intentional space. I think the data engineering team did not see this. So when you enter the close, you must ensure that there is a gap here, right? So length of the DF, I have 496 days of data. And if I had plotted that, this is how the trend of Bharti Airtel for the past 496 days. In stock market, for a year, you will have 250 days, which means I have about 2 years of data. From 2009 of July till now, I have 2 years of data. And we can see the stock has moved from 350 to about 530, 525 levels currently. Right? And we can see there is no seasonality or trend or anything. Of course, yeah, trend is there. Trend is together, it is at the upside. And we will predict whether the current trend is on the negative side or not. Right? It is at the verge of coming down. As we can see, this is the bottom. And if it falls below that, there are a lot of chances it will come down. Let's see what neural network model thinks about this trend, whether it will go up or come down. Right? So I'm creating a data frame. Airtel close is equal to df close. So this is my data set. And I'm resetting it. I have the date with me. So when I just filter that, it will come with the index value also. So the new data set will be having date also. So I'm just dropping the index, resetting the index and dropping the same so that I will have only one column. and I'm just making it as a data frame. Now let's do a train test split. The way you can do is the data dot index location, and starting from 0, I can specify as 0, and I can just leave it as it is, to 480th day. And the test data will start from 480. So if I say 480, it will start from 481, right? 481 to whatever the length of the data. I can specify as 496, but it is always safe to leave it as it is. Sometimes you may not know what is the exact ending of your data. You can just leave it as it is rather than checking for the same and updating here. Right? And what if your test data changes tomorrow? So it is always better to leave it as it is. Right? So I'm giving 480 days to my train and only 16 days to test. Right? I cannot give 70-30% here because I don't want to predict what will happen to Bharti Airtel for next 100 days. Right? That's not going to make sense. I don't want to keep forecasting over forecast for next 100 days. I very well know there will be too much of noise. So I've splitted the data. Now let's do a scaling. See, scaling is not required at all, to be honest, but still you can do, because when you apply some deep learning models, it is going to take some computational power. And if the values are within the range, the computation time will be lesser. Right? So it is always better to scale them, and they don't change the variance in your data set. Right? So doing scaling is not going to harm at all. It can be standard scalar or min-max scalar. I prefer min-max because this is always going to have a positive value, right? It will always be within 0 to 1, x minus minimum divided by max minus min. So it will always be within a 0 to 1. So that's why I prefer min-max scalar always. And scalar.fit, I'm fitting it on the train data set. When I do this, I will get the max value and the min value of the training data set. Once I do that, I use the same maximum and minimum to transform the train values. And I'm going to use the same maximum minimum of my train data set on my test data set. This is a common pitfall. I think most of your mentors would have already told this. When you do scaling, you first split the data set. You apply the scaling on the train data set, get the parameters. In terms of min-max, you will get minimum and maximum values of train, and you will project the same on the test data set. In terms of z-score, you will get the mean and variance of train data set, mean and the standard deviation, and you will apply the same on the test data set. That is for the case of z-score. Now I'm using the deep learning models from TensorFlow. This is the library for using a lot of deep learning models, Keras and TensorFlow. One advantage in using in Colab is that you don't have to install these libraries. It will come automatically. But when you want to install in your local machine, sometimes you will end up at a lot of errors. It requires some exceptions, and some libraries should be up to date. A lot of dependencies are there. Right? So it is always better to run these libraries in Google Colab. Only thing is you need internet connection. Right? From TensorFlow.keras preprocessing.sequence. Right? Under the sequence umbrella, we have n number of factors, and this is a sequential data which we already know. Right? So from there, I'm generating something called time series generator. This generator helps us to transform the values, and it will save in an array format. Right? We will shortly see what it does. And for any function, if you want to know what that function does, just do help within the same, pass in the function name, which is time series generator, and it tells you what it actually does, what kind of output that you can expect. And let's say this class takes in a sequence of data points gathered at equal intervals, which means on equal, let's say if it is daily, on daily basis, along with time series parameters such as length of the history to produce batches or training validation. Right? So what are the arguments it expects? The original data itself, and what is the length of the data that you are passing in. These are the two things that are required. What this will do is, let's say if I have 100 training data, and I want to give next 15 test values. So together I will have 150 data points, and the last 15 is basically the test data. Now I will have to validate it. I hope most of you know what is validation data set, right? Other than this is like a test data set wherein which we create, once again, we split the data into three: train, validation, and test. Before passing on the data to test, we will pass it on to the validation to once again validate the model. This was the traditional practice, and the same can be followed in time series as well. Right now, so you can go through this generated at your available time. Now let's pass on this. So I have 16 days of my test data. So I will pass on this length as 16. My batch size is 32. See, this batch size can even be 1. If I say batch size is equal to 1, at every iteration, the entire batch will be considered. If I have 496 days, the entire 496 days will be taken. But if I split them into, let's say, 10 or 20 or 32, the computational power will be very, very lesser. If I give 1 at a time, the model has to be run on all the 496 points. But if I give 10, it will run parallelly on all the data points, 50 by 50 by 50. Right? So the time it is going to take is very, very lesser. Right? You can always play around this batch size. See, this entire neural network, if you run once, you will get different result. And the second time you run, you will get second different result. In your own machine, the same codes, same data set. That is how the neural network works, right? The weight initialization is always random, right? So it is always better to iterate over each batch size and identify which is the better for your model. I started from 1, I kept 5, 10, 20. Normally for larger data set, people give 32. Of course, we don't have a larger data set here, but generally 32 works really well. Right? It can be 1 also. It can be anything. It is going to directly impact your computational power and the time. Now let's build a generator object, time series generated, your data set. This expects X data and Y data. And your time series, your data is X and Y, right? So that's why we give scale train, scale train. X is also scale train, Y is also scale train. Length is equal to 16, your test data size. The batch size is equal to batch size. Okay, this will create an object of train and minus length data. Let's say if my train data is 496, 16 days will be removed and 480 data points will be there. And the last 16 values will be predicted. That's why I give length of 16, which is equal to my test size. Right? Now I have the data set with me that is ready for model building. Now let's build the model. So from tensorflow.keras.models, import sequential. And from TensorFlow, import dense, simple RNN, LSTM, and dropper. We'll see what are these. Don't bother about these new terms. If it is new to you, don't bother about it. We will very shortly see what are these. Right? So I've brought in the important functions. Let's build the model. Like in sklearn, what we normally do, we first build the model object, then we will fit it on the train data set. Right? We will say model is equal to sklearn.logistic regression, open and close. Right? We will say some parameters and we will project it on the train data set. The same is what we are going to do here. Only that there are some more functions that we will add to the model. Model is equal to sequential. This is my initial model. And model.add, I'm going to add some parameters, which is my algorithm name is simple RNN. And the number of neurons that I give here is 30. So it has to be minimum 16. If I'm predicting 16 outputs, it has to be minimum 16 and it can be anything. Right? If I want to keep more layers, if I want to create more neurons, I can create more neurons. It can even be 100 also, but going for more neurons will overfit your model. Right? So I just keep it as 30. You can also try with 16 or 20, 25. Right? I tried it and 30 worked really well for me. And input shape, what kind of data are you going to bring in? Length, which is the test size, and the number of features. How many features are you going to bring? Which is only one feature. I have only one feature. Right? If you have a multivariate time series wherein which you have 5 x variables and only one target variable, then you'll have to specify them clearly here. Right? X dot shape of the number of rows and the number of columns. Right? Here we have only one column, so we've made it quite simple. The next one is dropout. This dropout is nothing but this helps you to overcome the overfitting issue. Rather than learning from all the data points, let's say if I give 0.2, it means it will not learn from one data point out of 5 data points in the past. Right? So that is what dropout is. This helps you not to overfit the model. Right? The default rate is 0.2. It's not just here. The overall dropout default rate is 0.2, and I've just used it here, and it really worked well. And I add another layer. By adding it, what we are doing, we are actually adding layers to the model. This is one layer, and this is my output layer. Dense is basically the output layer, which is just one. Right? I'm going to predict only one data point for every layer. For every day, I will have only one output, right? So dense is equal to 1. And model.compile, this is where I bring in the back propagation, wherein which optimizer is equal to Adam and loss is equal to MSC. So in terms of error, y minus y square, my error here is MSC, which is y minus y bar the whole square. Right? Based on that, the optimizer will start applying the gradient, and it will change the weights accordingly. It either increase or decrease. So get the model summary. This is my entire model. The model summary, it has 960 parameters, which is nothing but the input shape, the length into features, right? And once the model object is built, then we will put it on the data set, right? This is what we do in sklearn as well. Model.fit the train data set. Model.fit generator. Generator is the object that I've created here with my training data set. I'll just pass it this here. Epochs is nothing but the number of iteration, right? We will, the back propagation, we'll know how it actually works, and we'll have to stop at a certain level, right? If not, it will keep learning. So I'm going to fix a value that my number of iteration is going to be 10 times, right? If you give more number of epochs, your model will overfit. And if you give very lesser number of epochs, your model will underfit. Right? So you'll have to strike a balance between them. You cannot always decide which is a correct epoch. You will have to only iterate and look at the error, and you can see which one is a better one. Right? Essentially, I gave 10 here, and shuffle is equal to false. Why shuffle is equal to false? And this is a sequential data, right? I don't want to shuffle. And if you run it, this might take light of higher time than the ANN. So once I've run it, I can see in my each iteration how the loss is brought down. From 0.14, it has been brought down once again to much lesser level of 0.015. Right? This is my model history. I can get the same by pd.dataframe model.history.history. This function gives you the loss function. Nothing but these numbers. I can just save them as losses data frame, and if I just plot it, I can see the way the error is starting to come down. And if I don't give the epochs, normally how ANN works is, if the error is getting stabilized, the iteration will get stopped. Right? Instead of doing that, I've given manually the number of epochs, and it looks like at the 10th epoch, the error is at the lowest level. Right? I don't want to furthermore reduce the error. If I do that, I will overfit my model. That is why I said, if you give higher epochs, the model will overfit. Right? Now we have built the model. Let us create a batch, and we will test the same. So in my train data set, I will get the last 16 values. If I say minus length, which is 16, it will give me the last 16 values. Right? These are my last 16 values in my train data set. Right? And we will use the same values, and we will predict the next value. let's say this is 16 value, this is first test value. Let me predict the first test value, which is model.predict, the same that we've learned in sklearn. Model.predict first eval batch, which is basically the first value of this. And this gives me an output of 0.75. So the first actual value is somewhere around 0.79, and this is 0.75. About 4% of error here, but still looks like a good one to me. Now what I'm going to do is, the same way I predicted for first value, I will have to predict for all the 16 values. So I will have to apply for loop, right? That is what I'm doing here. I'm creating an empty list, test predictions, which will save all the predictions like this, and passing in the first batch, the last 16 values, and model.predict current batch for every first value. So it will keep predicting the first value. And this line of function will give me the predictions. I'm not going to spend too much time on explaining this. What happened is, as we speak, this code was there for past 2 years. As we speak, there is already a predict function that can do all this in TensorFlow. Right? I will also share that prediction code after this session when I share this Colab file. So you don't have to do all this heavy lifting. Just like what we do in sklearn, we just predict it and it will do all the data sorting, making it as a data frame or array by itself, right? So we have the predict function with TensorFlow also. So with that, you can do this quite easily. Once we get the prediction, this is a scaled value, right? This is not my original value. So to bring back to the original value, I can use inverse transform function. True predictions is equal to scalar dot inverse transform function, the min-max scalar that I've already saved before building the models, pass in the test predictions. So this gives me these values. So the predictions are 538, 529, 534, and it says the stock is likely to be somewhere around 528 after 16 days. Right, so let's just add this to my test data set. So this is my original test data set, and these are my predictions. And we can see there is a good amount of error, 546, 538, about 1%, 1.5% of error. Here it is 2% of error. Right, 545 minus 534, about 10 points, which is 2% of error. Right, but we can see at the end they are converging together. The error is coming down. But let's just plot the same, and this is the plot of this test value. I'm not plotting the entire data frame, and we can see it has picked up the noise quite well. Only that it has missed out some trends here, but it has picked up the learning has been quite intense. We can understand the comparison, and this is the final prediction. Right? This is my original value, and just the part that we are actually looking here is this part. Now we have 496 days, and we built model only on 480 days, and we predicted the next 16 days, and we are quite happy with this accuracy. Right? Let's build full model. When I say full model, I will learn from all the 496 days, and I will predict next 16 days. Okay. So apply the min-max scalar on the full data set, the entire 496, and create a time series generator like we did earlier. The length is equal to the same 16 days. Batch size is equal to 32. Build the model, sequential, simple RNN, the same features. I'm not going to change anything here. The same model, fit generator, and check for the losses. Once again, the losses are at a minimum level. Take the predictions. These are my forecasted values for next 16 days. I'm just adding them to my data set. Let me just. So full data is equal to pd.dataframe, np.concatenate, forecast.flatten. I'm using flatten here because I will get an output in a 2D array. Right? This is basically in a 2D array. We can see two squares here, right? So this is in a 2D array. I'm just using the flatten function to make it a 1D array. So after doing that, I'm just plotting the full data set. So this has next 16 days trend also. If you look at the original plot, Up till 500, this was the trend, and this is after 500, next 16 days. And it says the stock price is going to come down. And this was up till 29th July. The data I had was till 29th July. So this was, 29th June. This was the closing price on 29th June. And after that, the stock prices have come down. Right? And that is what is reflecting here also. And I said 29th July. So this is future. 30th July. 29th June was the ending date. 30th June, 1st July, 2nd July. And on 2nd July, my model says it should have been 516, but the actual price was 525. Right? There is a 2% error in this model. Right? So this is basically RNN that we have built. And one good thing about this is this was able to pick up the noise. Right? And 2% error is somewhere around you can accept. Okay. Now let's build LSTM model. What is LSTM? It will not forget the past values also. What if this kind of trend was there in the past? Let's say this kind of trend and this kind of trend. This is what we are having here. Right? If that is the case, what will happen? It looks like if that is the case, the stock price will come down drastically. Let's see if LSTM is able to say that the trend is going to be on the downside or not by remembering the past values. Right? And here, this is practically not required, but I'm just giving you, when you work on a very large data set, this is something you need. What is this? When my model accuracy is coming down, I don't want to look at this plot and decide which kind of epochs that I have to give. I want my model to automatically predict the epochs where the error will start to stabilize. Right? So if you look at this is once again from callbacks in Keras function, early stopping. I'm saying in terms of validation loss. In terms of validation loss, if the loss is getting minimized and stabilized, stop the epochs. Even if I given 50 epochs, if the error is down and stabilized at the 10th epochs, at the 10th epoch, the model will stop at the 10th epoch. It will not go up till 50th epoch. This way, I can once again ensure that the model is not overfitting. Right. So, and what kind of level I'm saying? I'm saying if for the next 2 epochs, the validation loss is not coming down, stop the iteration. Okay. So it will wait for 2. It's by default, it is 0. I can say 2. You can, if it is a very large data set, you can say 5 or 10 also. Right. Once again, this length and everything is one and the same. Let's build the generator here. One small requirement for LSTM is that the length should not be one and the same. It should be one data point lesser than that. Right? It does not accept the lost data point. So I've kept length as 15 and I'm building a generator here. Additionally, I'm also building a validation generator. While LSTM is running, it will also have to look at the validation error. Right? Earlier, we did not added this. So we are adding it here so that parallelly my model will also run the validation test and it will stop at the number of iteration where the error is minimizing. And if you look at this model, the way you can build, once again, sequential model.add, this is one layer. To this neural network, I've just added one layer and the output layer. I've not added multiple layers. This is a very simple data set. Right? So I'm bringing in LSTM, 30 neurons. Input shape is length, comma, number of features. Dropout is once again 0.2. And my optimizer is Adam and loss is equal to MSC. See, each parameter that you see in neural network can be tweaked. Right? They are not hard and fast rules. It's not that the dropout has to be always 0.2. If you want to take risk, you can say 0.4 also. Or if you want to say play safe, 0.1. There are different Adam optimizers also, different solvers that are available in Python. And loss function also, you can use map mean absolute percentage error or absolute error, right? You can change over different values. Then you build the model.fit generated. I have built the model object, then apply it on the data set, which is generated. I'm giving 20 epochs. I'm giving higher epochs because I've given the early stop mechanism. So if the epoch is better, then it will stop automatically. And validation data is equal to validation generator. So when this is building the model, it will also look for the validation error. Based on that, it will stop. So callbacks is equal to early stop. Once again, shuffle is equal to false. Right? And this says at the 6th epoch itself, the validation error has brought down and it believes that further epoch is not required. Right? So this is the benefit of early stop. What is the difference between dropout and early stop? Dropout is basically to forget something in the past. Let's say if I keep 0.2%, out of past 5 values, 1 value will not be considered for my learning. Right? Why am I doing this? Because if my model learns all the past 5 days, there is a chance for overfitting. So you can avoid this also. You can run the model without this also. There is no error. But if you want to, when I ran this model without dropout, my model overfitted. So I just used the dropout here. Even when I used this, there was a chance of overfitting. As you can see here, the loss was here and the validation loss was much lesser. Right? There was a chances of overfitting here. So that's why I earlier used dropout and brought down. Earlier it was even worse. So to answer Sunil Kumar, the scaling is not required. That is what I said. Scaling is really not required, but this is a practice of making. Let's say you work on some data which has 1 lakh values and it is going to take too much of computational power, right? When you calculate the MSC values will be very large, right? It is only going to take too much of computational values. But if I keep them in a scaling, the computation will be very, very lesser. That's why we scale it. And as I said, it is not compulsory. It's up to your own wish, right? So the validation loss is attractive. So I can go ahead and predict the same. I'm predicting the same using the same line of codes, which we earlier used. I've also given the explanation here. If you want, you can just go through, run everything, print everything separately and understand what each line of codes are doing. But this is nothing but location, array location and reshaping the values. Okay. I've done the predictions. I will just inverse transform them. And when I plotted them, the RNN had actually worked really well, but the LSTM is far beyond the levels. Right? It is way out of the league. The actual values are blue ones and the LSTM is way below that. Let's understand why that is the case. Right? This looks like a poor forecasting. I honestly agree that this is a poor forecasting, but what happens here, let us understand. I'm forecasting the future also. Now I'm okay with this model. I will explain very shortly why I'm okay with this model. I'm going to forecast the future. The same formula, the codes and everything is one and the same. I'm just forecasting, inversing them, adding to the data frame. And this is how my original, the forecasted values are looking like. It says the stock price is going to fall down. And why it is the case? Because see, I can able to interpret this because I know the domain and I don't know this model as well. I know the Bharti Airtel as well. This is something that every day morning when I wake up, I look at this stock. And LSTM, even though this forecast looks weird to you, it has smartly picked up the downtrend that is going to come in Bharti Airtel. I'm not sure about it, what's going to happen tomorrow in Bharti Airtel. But if you look at the past events like this, which I shown earlier, this kind of trend, in this kind of slide, Bharti Airtel never have came up. Okay, only at a far below level it had came up. But other than that, most of the time it have come down. And in terms of memory, LSTM was able to pick up that and it is actually giving you a downtrend. Right? And this was one of the smart things with the LSTM. And if I had run more epochs, see when we got this output, I had ran the model with 10 epochs. But here I had ran only about 6 epochs. Maybe if I increase my epochs, look at this, I have only 6 epochs. So if I increase my epochs, probably my model might perform closer to the actual values. Right? That is something I can iterate over different parameters, but I'm quite okay with this. I'm going to select RNN as my best model only for this data set. Why? Because we can see more number of times Bharti Airtel will go into a range bound, then it will react. Then it will go into a range bound, then it will react. Most of the time it is within a range bound. So past 5 days or 10 days values were dictating the next day value. That's why RNN is more than enough rather than memorizing what happened past 2 years before. Right? But LSTM came in additionally and said there is a chance of downtrend, which your RNN was not able to say. Your RNN is saying the stock price is likely to go up. There is a chance that the stock will come down. But look at this prediction of RNN. What does it tells you? It is likely to go up and come down, which was not there in the training data. And it actually worked in the yesterday. It all of a sudden went up and it came down. Right? This was slightly picked up by RNN, but of course, as I said, don't take it as a recommendation. See, you can never forecast anything in the stock market. Right? There are thousands of algorithms, thousands of geniuses that have been in the stock market, but you can never say what will happen tomorrow. But you can build tools to most probably say what you can expect tomorrow. Right? That is why we do all these things. Tomorrow, what can happen? So I will have a probabilistic view on what can happen tomorrow, and based on that, I can take some precautionary actions. Let's say I am an investment banker and I handle a cash of 1,000 crores, and I cannot simply believe my intuition. Right? I need some technical tools to say what will happen or what might happen tomorrow. That is where you can use these kind of deep learning models. Right? And this trend says after 16 days, Bharti Airtel is likely to go to 512 rupees from June 29. So which means somewhere around July 20, because I'll have to neglect the Saturdays and Sundays. So around July 20, LSTM says Bharti Airtel is likely to go to 512.40. Right? Maybe check the next week or the next to next week of prices. You will understand this and see whether this model is powerful or not. I'm just thinking the prices are likely to come down. Let's see what happens in the future. And this is not in the academics. I'm just giving you another model, which is Facebook Prophet model. This was built inside the Facebook only, and this was particularly focused on very short-term data, like 1 minute data, 1 hour data, 10 seconds data. Facebook wanted to predict how many events will happen in next 1 hour throughout the world. And some employees in Facebook, they created this model, which is called as FP Prophet. Right? Let's not go too much into this. Even the people who have built this have not given complete details about it. But one good thing about this model is it is very simple to apply. It just needs your X variable, which is date, and the close, which is your Y variable. I am saving it here. And date should be saved as DS and close be saved as Y. This is one of the requirement for this library. So I've renamed them. Then just apply the model, that's all. The way you can apply this Prophet, change point scalar, this is some degree of change that I'm giving. And daily seasonality I'm giving as true here. Right? This is a daily data, so I'm giving daily seasonality is equal to true. Of course, there is no seasonality in the data, but I'm just giving some parameters to test what is going to happen. And if you get the predictions, just follow this codes. These are very simple. This is the only line where you can predict the future. Think about LSTM, where we gave a lot line of codes, but in FB Prophet, this is simple. Right? These are just customizations. And FB Prophet is also saying that the Bharti Airtel price is going to come down. Right? All the dots are actually the actual data, and within which it have found out some trend. And based on that trend, FB Prophet is also saying the Bharti Airtel is going to come down. My LSTM is saying the same, and my FB Prophet is saying the same. Let's see what's going to happen in next 2 weeks. right? I'm quite sure you will all be looking at that price. Just go to Google, check for Bharti Airtel share price. Let me know how it went. Okay, and this model once again can be decomposed. And when I decomposed it, this is the trend that the profit model has identified. And in terms of weekly seasonality, there is no seasonality. And it says sometimes on Thursday, the stock price comes down, on Friday, it goes up. Right? And daily seasonality, there is not much to look at this. This is a daily data from morning to evening. We don't have hourly data with us. So we'll just have to ignore this. Right? So, great. And I think this is it, guys. I hope the session was useful to you. I will just run through the questions that I received. I think I've answered most of them. Yeah. So why did I choose this company? Because I know I've been. You will also know for the next 1 month. This stock is always in a range. Right? This will always be in a range. There will be some sudden movement, then it will always be in a range. Right? If you look at some other stocks, they will not be in a range. Let's say Adani Ports, for that matter. You can select any stocks, they will. So this is also in a range. I'm not sure what kind of, let's say, Reliance Infra. Or let's get the Reliance Sharp. Right? They are not in a particular range. They always keep moving. And Reliance Infra, maybe this was in a trend. And right, see, these kind of stocks are always on the move. Right? You cannot predict the same. Right? Each share price. Someone wants to see each share price. Once again, this is always on the move. This is not on a break-even range. Right? It will always not be within a range. You see, you can also predict ITC. ITC and Bharti Airtel these days are one and the same, and we can see it will be in a range, then it will move, then once again it will be in a range. Right? You can apply the algorithm on ITC also. And I applied it and it said ITC is also likely to come down. So that is the reason I selected Bharti Airtel here. But you can ask me one question: what to do if my stock is moving all the time? Let's say I'm not sure if SBA is right. SBA is also moving. It is always in some trend, right? If that is the case, what can I do is I'll have to create a stacked model. I will create another layer of model here. Let's say I will say model.add. See what is hidden. Why do we use hidden layer? Because our learning has to be deep. Right? So for a data that has too many noise, you need more hidden layers, right? So that is where you can add another layer of LSTM. Then you run the model. Right? For this data set, I did not require, but if your model has too many noise, or if your data set has too many noise, you can use the same. Right? By this, this is basically called as stacked LSTM. I will just this is basically stacked LSTM. So you are further deepening the learning so that the model will pick up that noise also. Right? So yeah, some technical indicators, let's say you can take, see the NSE is starting to give a lot of technical indicators by themselves. If you look at this, VWAP itself is a technical indicator, and give it another 1 month or 2 months, you will get all the indicators in this data set itself. Last year, only these values were not there. If you get the historical data, you will only have these. Right? You would have seen these data in the business line paper also some years before. So that is the thing. Some good reading resources for LSTM. In terms of underlying math, I would recommend Machine Learning Mastery. This website is very, very good. Not just for, I guess this is like, I'm not promoting this page. So let's say this person I think I've always admired, and he talks each model from the scratch. Right, you can also build logistic regression from the scratch, random forest from the scratch. Right, you rely on the model function, right? From sklearn, you will just bring in the model function and you will right away build it, right? But if you build from scratch, you will know the nooks and corners of each models, right? So this guy would have built each model from the scratch, and he is very good for understanding the LSTM also. You want to learn linear algebra, you want to learn hypothesis, you want to learn probability. I think this guy is very good. So I would recommend this.
Now let us very quickly summarize today's video. In today's video, we discussed that artificial intelligence project refer to the various projects that you learned in this tutorial. We started off by understanding how using ANN we can understand bank defaulters, then learn about stock price prediction. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.